the recording. Thank you. All right, well, we'll get started. Just to welcome everybody back to day 3 of the working group meeting. It's always good to a good reminder of even virtual meetings can be exhausting, even more so when you're juggling all the typical stuff at home and at the office that you generally get away from when you get to travel. So just a reminder of some of the logistics. We have a variety of talks today, and I'd like to encourage each of the speakers to, of course, plan to share their own screen if they would like, but if not, make sure you've sent Elizabeth the backup slides just in case there's any issues. To try to leave at least a few minutes for questions at the end of your time slot. But for each of the breaks today, or for each of the general breakdowns today, we do have some time saved for discussion at the end, but we would like that to kind of be more general discussion. And then we do have a longer period of time at the end of today's talks for a broader kind of all hands across all the working groups discussions to talk about the successes and gaps and future needs as based upon all of the results and discussion we've had the last 2 days. So just a reminder, if you have questions after the talk, feel free, or during a talk, feel free to raise your hands and I'll call on you after the speaker is completed, but also feel free to continue using the chat to ask questions as we've been doing the last 2 days. So with that, this morning, before our first kind of lunchtime break for some of us, we do have 2 sessions this morning. The first is based upon insights from kind of model intercomparisons or a variety of model simulations. And then we'll also have a session on dynamical cores and physics dynamics coupling within the atmosphere models. So we'll go ahead and get started on our first session. So our first speaker is Joachim Paeko, who will be talking about wind turning in the boundary layer and CMIP6 models. So Joachim, do you want to try to share your screen?
Yeah, I will do that. Can you hear me properly?
Yep, can hear you perfectly.
Nice. Right. Give me a second. Okay. Can you see my screen now?
Yep.
And if I do a presentation mode like this, can you still see it?
Yep, it's perfect. Take it
nice. Away. Okay, great. Here, okay, whoops. All right. So hello, everyone. So my name is Joachim Paeko, and I'm going to be presenting some results from a study that we are sort of on the verge of starting the publishing process on, which is about evaluating wind turning in the planetary boundary layer in models participating in the coupled model intercomparison project version 6, or CMIP6. So just some real quick info on myself. So I'm a PhD student at the meteorological department at Stockholm University. And my supervisor is Gunilla Svensson, professor in meteorology. And my PhD thesis is about the evaluations and improvements of momentum fluxes and related processes in the boundary layer. So to start, let me quickly define sort of what I mean by the boundary layer wind turning. It is the directional difference between the surface winds and the winds just above the boundary layer. We first need to find the boundary layer height, which we do by calculating the Richardson number at each height in the models, as shown in the equation right here. We have, for example, the virtual potential temperature at the surface and at some height z, and the wind speeds at height c. And we use that in this equation. And we also, we define the boundary layer height as the first height from the surface where the Richardson number exceeds a critical value of 0.25. And we also, in the models, do a linear interpolation to sort of find a better estimation of the boundary layer height. And I will be referring to this method as the bulk Richardson method. So for the models, we chose 8 different models, plus the ERA interim reanalysis. And the reason for using ERA interim is because we wanted to compare our results with results from another paper on the global climatology of wind turning angles in observations by Lowlevel and Ensemble. And the CMIP6 models I've listed here, they include, for example, the CESM-2 model, but that can also be seen in the legends of the plots that I'll be showing. But the time period is that we used is from 1981 to 2010, but only 2000 to 2005 for ERA interim. And we also include some observations in the study, and those are from the same observations as used in the paper by Lowlevel and Svensson that I just mentioned. And they're from the Integrated Global Radiosonde Archive, or IGRA. And we use about 800 stations global, and that data is from 1971 to 2010 in our study. So there is, of course, some variation due to variable data availability in the different stations, but the stations can also be seen in this little figure right there. But let's jump straight to some results that we found. And here we have probability density functions of wind turning angles at the IGRA sites, or the closest grid points in the case of the models. And we also include both the northern hemisphere and the southern hemisphere, but the wind turning angles signs are reversed for the southern hemisphere. And so the full lines in this plot shows the models, and the dashed line shows the observations. And what this sort of tells us is that the model distribution is much narrower than the observed angle distribution. And although some of the models have broader distributions than others, for example, the GFDL CM4 model has the broadest distribution, I mean, closest to the observations. And in this case, the NORI SM2 model has the most narrow distribution. But moving swiftly on, we have some maps showing sort of the global distribution of median wind turning angles during the entire time period for each model also. So we see sort of mainly what is to be expected of the wind turning. It's positive or clockwise turning with height in the northern hemisphere, and negative or counterclockwise turning in the southern hemisphere, with some exceptions, of course, in certain locations. But there's not only a difference in the magnitudes of the wind turning angles between the models, but the land-sea contrast is also different in each model. Let's say. Now we also look not only at sort of the wind turning angle throughout the boundary layer, but also the flux of mass across isobars in the boundary layer. And this is kind of a nice quantity because it sort of just gives us a bit of a number on the behavior of the boundary layer for the flow. And it is calculated by integrating the density and the ageostrophic wind throughout the boundary layer. So a positive value would mean a flow towards lower pressure, while negative values would mean a flow towards higher pressure. And in our study, we use the wind just above the boundary layer as the geostrophic winds in the models, assuming no change of the geostrophic wind with height in the boundary layer. So we see, for example, that there are, in all of the models, there are several locations of negative mass fluxes, such as, for example, the North Atlantic storm tracks. And I can't say that this is, I can say this is unexpected because there aren't that many studies of this particular variable on this scale, but it has a lot of interesting implications for sort of the developments of and yeah, lifetimes of low and high pressures. And I also want to point out that there is one model that sort of sticks out here, which is even from, or it is the ASM2 model, which is similar to the CESM-2 model in that it also uses the CAM6 model, but atmosphere model, and still it's quite different, and it just sticks out from the rest of the models, and also ASM2 in general sort of had the low wind turning angles, and what I also haven't shown here is that we found that it also has quite low boundary layer heights in general, at least using this methodology that we've been using. So things like that sort of made us wonder what would happen if we used a different method for finding the boundary layer height. And we tried just using the pressure level of 850 hectopascal as the boundary layer height, sort of to see what would happen. And this plot sort of shows the same thing that I showed earlier, but in this case, the dotted lines also show the distributions with this 850 hectopascal level. And we see that all models get a distribution that is much broader and thus closer to the observations. And using this methods on the observations, however, did not change the results much at all. And so lastly, if we look at the same types of mass flux maps that I showed earlier, but with this 850 hectopascal method, we also see a general increase in the magnitudes of mass fluxes in all models. And this means, in this case, that by using this sort of bulk Richardson method, we are missing a significant or a substantial amount of information between the boundary layer heights we find there and the 850 hectopascal level. Also note how the ASM2 model no longer sticks out. So in summary, we find that we have general underestimations of wind turning angles in the boundary layer in all models that we've used. We also found several significant areas of negative mean mass fluxes. Also, the bulk Richardson method that we used here, which is a tried and true method for diagnosing the boundary layer height, seems to give us more underestimations than we perhaps would get with other methods. And lastly, some models stick out, particularly the ASM2 model with the bulk Richardson method, even though it uses the CAM6 atmospheric model that CESM2 uses. And we speculate that the differences between the two might be due to the tuning of some parameters in the club scheme made specifically to the ASM2 version of CAM6. But yeah, thank you for listening.
All right, thank you. Do we have any questions? So there is a question actually in the chat that came through from Julio Backmeister that asks, do you have a physical explanation for how the PBL mass flux can be negative?
Yeah, we have some speculation sort of on how they can occur. There are, like, for example, we have some assumptions that sort of, for example, like I mentioned, we assume that there's no change of the geostrophic wind with height in the boundary layer, which can also sort of affect the results. But the sort of physical implications in this case, like I said, it's that we have flow towards, if it's negative mass flux, it's a flow towards higher pressure. So it sort of strengthens, I guess, the higher pressures. But I can't come up with a proper physical. I don't have like an answer for like a proper physical mechanism for how this works yet, at least.
Great. I see that Rich raised your hand. Rich, do you want to unmute and ask a?
Yeah, I was just wondering for the cross isobaric component you showed, it was a little tricky to tell because you showed the full fields, but I'm wondering if there's a common problem amongst the models that, you know, could be understood. Is it related to like common SST biases over the ocean or something?
That I'm not sure of, actually, to be honest. It's because this study has been, it's like what we did or what we used in this case was just we used the fields of temperature, temperature, the humidity, and the winds, U and V components of the winds, and produced these results. And honestly, I haven't looked too much into sort of the specifics about model biases or stuff. Yeah.
Thanks.
I have maybe a pretty basic question. I'm curious if you've looked to see if there's been any differences in the number of kind of model levels that are in the different boundary layers for these models, to see if there's any.
Oh yeah, I haven't I haven't added that plot here, but I actually do have something that sort of shows how many sort of model points that are sort of present in the boundary layer. Yeah, and that sort of varies quite a lot. For example, the ESM-2 model that I've been talking about has only very few points in the boundary layer. That, while, for example, the EC Earth model has like a lot of them. So yeah, we do have.
So, but it doesn't. Yeah. So, but it doesn't seem. I guess the general characteristics and the kind of PDFs that you showed. I mean, I guess it doesn't. It's not clear if having more boundary layer levels helps in any of this kind of.
No, not very clear. No. Although, I mean, if it's very few, then you can start seeing some really weird effects, like, for example, ESM-2, I would say.
Great.
Yeah.
Okay, if there are no more questions, I think we'll move on to the next talk. So thank you, Joachim. The next speaker is Levi Silvers, who is going to talk about the response of the large-scale tropical circulation to warming using some idealized simulations, I believe. So, well, I shouldn't believe, I should know. Levi, do you want to go into presentation? Yep, perfect. We can see you, and then you just want to make sure you unmute, and then you're good to go.
Right. Let's see. I went forward.
Yep.
Oh, this is going too fast. Hold on one second. The presentation mode is it's just going. It's cycling through, right?
Yeah.
Okay. Hold on one second. Sorry, everybody. Escape out of that. Just go.
Yeah, you could just, if you want to just go in this mode. Oh yeah. Okay, that works.
Okay. And then, all right. Thank you. Sorry for that delay. Thanks for the opportunity to present this material here. Hopefully some of you find it to be interesting. It's a little bit of a part two. I presented some of the preliminary stuff last meeting in the fall. And so this is a follow-up with that, and then showing some further work that's been done. So the title is what we'll focus on here, the response of the large-scale tropical circulation to warming. And then the part two is the title from last year. So this is work that I've been doing along with Kevin Reed, and also working with Allison Wing to sort of make sure that we're understanding RC-EMIP correctly. So this is very brief, just kind of a few of the basic details. The questions, so RC-EMIP stands for Radiative Convective Equilibrium Model Intercomparison Project. And if you have more questions about that, I'd be happy to talk about it, but I'm going to kind of breeze by it. The primary questions we wanted to address with RC-EMIP are asking whether or not atmospheric models of RCE converge to a robust climate state. Do they all do the same thing in the end, given the same experiment? And then another one is, what is the response of clouds to warming and the climate sensitivity within RCE? The hope being that if we could understand complicated things like clouds and climate sensitivity in RCE, maybe we could do a better job of increasing our understanding in more comprehensive models of the Earth system. And then also, perhaps most importantly, can RCE simulations inform future model development? So the model configurations in RCEMIP are global parameterized. There's a bunch of different types of models, and so it gets confusing quickly if you're reading through the papers, but there's global parameterized models like a GCM, there's cloud resolving models, then there's large eddy simulation models, and there are also single column global cloud resolving models. This study, everything that I've done is just looking at a global parameterized GCM like CAM6, but run in RCE, and also cloud resolving models in a large domain. So hopefully that simplifies that for you. And then to kind of recap what I started to present last year, this is the paper that's now finished that I think had been submitted last fall. But anyways, it's Kevin Reed was the lead author here. And we just sort of expanded some of the basic analysis from earlier RCEMIP stuff to look more in depth at CAM5 and CAM6. Another big point of that paper was to document the release of the QP RCEMIP comp set, which is now available for everybody to use. And so we are also using that comp set to kind of expand things a little bit. I'll talk about that at the end as well. So that's documented in this paper. And then a couple of the main points from that paper are that what kind of jumped out to me is that despite this, what I would say very substantial differences between CAM5 and CAM6 in the physics parameterizations, CAM6, for example, has club, CAM5 did not. The convection, while still using the Zhang-McFarlane deep convection scheme, I believe it was kind of retuned or reformulated a little bit in CAM6. And there are some other major differences as well, but they have the same dynamical core here. They're both using the SE dynamical core. So I was struck by how similar they are in the RCEMIP ensemble of models. These two, CAM5 and CAM6, really looked similar, and I was expecting them to be different because the physics are so different. And that could be pointing to a very large role for the dynamical core. I guess people on this call probably have different opinions about that. But I think that's an interesting result. And so here I'm just showing you precipitable water anomalies for one of the SST experiments for RCEMIP. And you see that there's sort of similar spatial scales and magnitudes of precipitable water anomalies. Then on the left, you can see the relative humidity profile for all three of the SST experiments. So the thin lines are 295 fixed SST, then we go up to 300 in the medium lines SST, and then the thick lines are the 305 Kelvin SST. And so this is showing that the two models basically have a similar domain mean profile. And if you're tempted to think that this domain mean profile is, which is on the order of 5 to 10% difference between the models, is a large difference, then look at the model ensemble in RCEMIP of all the different models that did these same experiments. This is for one SST, and you see that the spread among the models of relative humidity is more like on the order of 50 or 60 percentage points. So this is either strongly depressing or quite exciting, depending on how you want to look at it. But it's remarkable how much of a difference there can be, but not between CAM5 and CAM6. Another thing I thought was really sort of a big take-home point from that paper was that a difference between CAM5 and CAM6 is in the low-level clouds. And so here I'm showing you the cloud fraction and also the cloud liquid for all three of the SST experiments in CAM5 and CAM6. And we noted that in CAM5, there's substantially more low-level clouds. CAM6 really kind of misses this whole low-level cloud peak. And we did a little bit of sensitivity experiments looking at the, I believe it was the gamma parameter that looked at the distribution of vertical velocities. We were thinking that the club boundary layer was a bit too diffusive, and so it was fluxing liquid water out of the boundary layer too strongly, and that's what sort of led to this upper level peak. And so if you play around with that, you can get the low level clouds to sort of start to appear in CAM6 and look a little bit more like observations or CAM5. But one of the things that I thought was interesting is that if you then take the CESM-2 and 1 and look at CAM5 and CAM6 in the pi control and AMIP CMIP experiments. So then we're taking basically a full Earth-like simulation that's coupled with pi control and a full Earth-like simulation that's not coupled but has prescribed SSTs. We see these same differences between the two different generations of models. So this is looking only over the ocean between 5 north and 5 south. So we're trying to grab a region that should be similar to RCE. And so we see that this kind of big difference in the low-level clouds is mirrored in the parent models. which I think many people suspect to often be the case with RCE, but it was interesting to kind of show this and document it. And I think this should be encouraging for the usefulness of RCE, because I think it gives us hope that by better understanding the RCE cases, we can inform the parent model cases. Okay, so now moving on to the work that was beyond that paper. I wanted to look at the overturning circulation with the ultimate goal of a better understanding how the overturning circulation and the clouds interact. But right now we're really just focused on what happens with the overturning circulation in the RCE-MIP models. So I'm going to show you results from the model Ensemble, and then I'll sort of try to point out CAM5 and CAM6 so you can see where it lies in the range. But first, a little bit of background. There's basically two different ways that the overturning circulation has commonly been quantified in the literature. One that I think is possibly the most common goes all the way back to Betts and Ridgway, where you sort of look at the thermodynamics of precipitation changes and water vapor changes, and you look at how that changes with warming. So I've chosen to use this terminology of the water vapor cycling rate, and that is going to be equal to the rate of change of precipitation over the rate of change of precipitable water in a warming climate. So this is the same argument that was used by Held and Soden in their 2006 paper, where they talked about the overturning circulation decreasing with warming. This figure here on the top right comes from the Held and Soden paper, and you can see here they're showing the boundary layer mixing ratio, how it changes with warming, and this line, the diagonal line, is the Clausius-Clapeyron around 7.5% per Kelvin. And then here on the right, so each of these dots is a different coupled model. Here on the right are the same models, and it shows you the precipitation change, and you can see that it's substantially less than the Clausius-Clapeyron relation. So the way that this argument works is that if your precipitation is changing at a smaller rate than your precipitable water, which is shown to be the case here, then your cycling rate will have to decrease. So the rate of mass flux out of the boundary layer has to decrease with warming because of that difference between the two rates. And then this is a plot that came from Vecchi and Soden, where they looked at coupled global models, and they used this same relationship to infer the mass flux in a warming scenario. And they showed that all of those models decreased their overturning circulation, but to varying degrees. So I think this has been commonly known in the literature for a long time. What I was curious about is what does this look like in RCE models, and how robust is it? I need to really speed up, so I'm going to. So this is the models we used. The CAM5 and CAM6 models are these two light green dots. So everything I'm doing, like I said, is with GCMs and CRMs in the RCE-MIP ensemble. So here's sort of the same kind of scaling that Held and Soden used in Betts and Ridgway. You can see the precipitable water change on the vertical axis and the precip change on the horizontal axis. And there's quite a large spread, more than I was expecting, but that's, I guess, an interesting feature that is worth diving into more. And so then if you plot the cycling rate of water vapor, you can see that with all of these models, or with most of the models, I would say it's decreasing as the surface warms. And so here you can see that the inverse day timescale comes out to about 5 days up here, and it'd be 10 days down here. So you can see that the amount of time the water vapor is staying in the atmosphere is increasing with warming. So then this is the second measure of circulation that we looked at. This is a little bit more dynamic. This is looking at the 500 hectopascal vertical velocity, and it's looking at the mean upward vertical velocity and the mean downward vertical velocity. And looking at both of those two together, you get this value here for the different models. And we see, first off, a very wide range for any given SST. We've got values that are on the order of 50 hectopascals all the way up to close to 130 hectopascals per day. And then most of them are decreasing with warming, although not all of them. There's this case here and a few other cases where they increase. The CAM5 and CAM6 models are these two here, and you see that they actually are both increasing over the first warming period, and then they decrease over the second warming period. So the models don't have to decrease their circulation intensity with warming, but most of them do most of the time. This is another way of looking at it, and I'm going to kind of skip through this quickly because of time, but what this is showing is that most of this variability is coming from the mean upward velocity area rather than the mean downward velocity area. So here, what I wanted to look at also is to try to understand, so the the range of variability in the circulation intensity itself is mostly coming from the range of variability in the upward mean velocity at 500 hectopascals. What about the change? What about this rate of slope here? What explains that large range of variability? And this is showing that the slope of the circulation intensity is best explained by the slope of the upward velocity here, the way that the upward velocity changes with SST. And this is the downward mean velocity, and this is the diabatic mean velocity. And so there are relationships here as well, but the strongest relationship by far is the relationship with the slope of this upward velocity. So when I started out this study, I was very interested in sort of the clear sky regions and how the subsidence velocity or the diabatic velocity in those regions, how connected is that to the overturning circulation? And this figure is a little bit of an attempt to try to see in the RC-EMIP models, is there a large spread in the net radiative heating of the atmosphere or in the static stability? Because we know that those are two different ways that you can connect sort of the deep convective regions with the subsidence regions. And so this figure here on the vertical axis, it's just a scatter plot between the net radiative heating and the static stability. For all three SSTs, the increasing marker size shows you the increasing SST. And the take-home point of this figure is basically that both of these quantities are varying quite a bit in RC-EMIP. So the net radiative heating is kind of all over the place, and the static stability is varying a lot as well. I think it would have been interesting if we could have traced this variability to just one of these two factors, but that's not the case. So then another way of thinking about the RC-EMIP results is looking at what they simplify. So if we're given fixed SST, if we're given constant installation, no imposed large scale circulation and no land, you can ask, well, how similar are the surface fluxes of energy going to be? Hopefully they'll be a lot more similar with less of a range than, say, a historical simulation or something that's not quite as constrained. What we find is that that's not the case at all. We actually have latent heat fluxes. This is looking at the RC-EMIP ensemble for just one of the experiments at SST of 300. And the latent heat flux varies in some cases between 130 watts per meter squared all the way down to 60 or 70. The precipitation varies a lot. This Bowen ratio is the ratio of sensible and latent heat flux. So it's telling us that most of the variation is from the latent heat flux. But I'm really kind of astonished at how much these low-level fluxes are varying among the models. And I think this points to a really important role for low-level winds. So the conclusions are that most but not all the models are showing a weakening of the overturning circulation as the surface warms. That's what we expected, but it was interesting to sort of see it in RCE because this overturning circulation is not the Hadley cell, it's not the ITCZ. This is really just RCE with fixed SSTs, and we still get that same response, which I think points to the fundamental, the really fundamental nature of that decrease with warming. Then the large range of variability is explained by the upwelling velocity and also by the change of upwelling velocity. And then the correspondence between the RC-EMIP results with CAM5 and CAM6 encourages the use of this QP RC-EMIP for process studies and tuning experiments. These results can be found in these two papers here. One is submitted, but the preprint is available. I'm out of time, right, Kevin?
Yep.
Okay.
Right.
So these are the further conclusions. I'm not really going to read them, unfortunately, because I ran out of time, but I'll just say thank you and just send me questions if you have them. I see some in the chat. So
there is one question in the chat, and maybe it's just a quick clarification. So Adam asked a question about if the slope, the delta omega up over delta t is greater than 0, what does that mean physically? And I think Brian answered the question, but maybe I don't know if you're reading it and want to just recap what that means for the broader group.
If the slope of delta omega, oh well, Adam, are you getting hung up on the sign of it? Because the sign is a little bit arbitrary.
I'm getting hung up on the sign.
Don't get hung up on the sign. Just go with your physical intuition. So we have the upwelling regions and the subsidence regions, and
so Brian suggested that basically, as you warm the climate, the sort of resolved upward mass flux decreases.
That's right, and that's largely because the precipitation rate is relatively low relative to the rate of increase of water vapor.
Okay, thanks for clarifying.
Yeah. The sign is confusing though, but it's relatively arbitrary. That's why I say don't get hung up on it, but it is confusing.
Okay, so there are a couple more questions, which maybe we can stick to in the discussion at the end, because I think some of them are really good for a broader discussion about how we can use the type of analysis presented in this section for maybe tuning of models. So thank you, Levi. We're going to go on to the next speaker, who is Michael Morris, who is going to speak about the representation of extreme wind events in reanalysis and models. All right.
All right. All right. You can see. All right.
Yep.
Perfect. And it's a full screen, not the presenter.
Correct.
Okay. Awesome. Right. All right. So, hi everyone. So, as mentioned, my name is Michael Morris. I'm a PhD student at the University of Toronto in Paul Fisher's group, and like I said, I'll be talking about the representation of extreme wind events in models and reanalysis. So, just a quick overview of my talk. First, I'll talk about the motivation and some of the background for my work. I'll talk about some validation of the extreme winds in the ECMWF product. So I'll talk about both the AER5 reanalysis and a high resolution operational analysis product. Also to look at some large scale drivers of extreme winds using composites over these like larger fields in reanalysis, and then compare the, compare the results from the reanalysis to what we see in some CESM simulations. All right, so the motivation for our work comes from an application in structural engineering. So they're interested in how wind loads on tall buildings will change with a changing climate, and they've in particular they're interested in how a quantity called the design wind speed, which is just the 50-year return period, annual maximum wind speed, will change under climate change, because this is an important input for their things like wind tunnel testing or also computational fluid dynamics simulations. So of course, to get these climate change projections of extreme wind speeds, we'd like to be able to use climate models to produce these projections to see how climate change will affect extreme winds. Unfortunately, there is quite a great deal of uncertainty around these climate change projections of how extreme wind speeds will change. There are studies that have projected basically small increases or small decreases for extreme winds in North America, but the changes are generally smaller than the uncertainty. So to sort of illustrate this, I chose this figure from a 2012 paper from Sarah Pryor. And so they looked at a number of dynamical downscaling experiments with different RCM and GCM combinations for a couple different regions in North America. And this shows the percentage change in this 50-year return period, annual maximum wind speed. And so you can see, like, for example, this Pacific Northwest region, this model indicated by the blue dashed curve has most of its probability density for these projections above zero, indicating an increase in extreme winds, but many of these other models project decreases, and that's sort of consistent for a lot of these different regions. So you can see there's quite a great deal of uncertainty on how climate change will affect extreme winds, and there isn't even really a clear sign of the change. So one reason why we think there might be such a great deal of uncertainty around how extreme near surface winds will change is simply because climate model representation of near surface wind speeds are quite biased. So I've shown here for a particular location in Toronto, where I'm from, a comparison between observed wind speeds in black, results from the CSM large ensemble in blue, and AER5 in green. And you can see that these distributions are quite a bit different. And in particular, the two model-based products have much lighter tails in the observations. So they might be undersampling these extreme winds. So if climate models are not doing that great of a job at simulating extreme near surface wind speeds themselves, might there be something we can learn about these extreme events by looking at some other larger scale, perhaps more well-resolved variables in these climate models. So what we're going to do is basically bridge information from station observations of extreme winds, reanalysis, and results in a free-running climate model to try to examine the scale and the character of these extreme wind events, with the hopes of being able to try to produce some kind of constraint for climate change. So before we can look at the reanalysis to study these observed extreme wind events, we need to make sure that our observed extremes are actually showing up as extremes in the reanalysis. So we've already seen that AER5 has a low bias of near surface wind speed. So what we're going to do to try to define extreme wind events is choose the events with wind speed above the 98th percentile in a given season in the given product. So an observed extreme will be above the 98th percentile of the observed wind speed distribution, and an AER5 extreme will be an event with the AER5 wind speed above its 98th percentile. So I've highlighted here in these scatter plots are these extreme events, and in the darker blue shows when there is an observed extreme event that is also captured as an extreme in ERA 5 within some short time window to allow for some temporal disagreement. The lighter blue dots show the extreme events at the stations that are not captured as extremes in ERA 5. And so the percentages in the caption, so the percentages of these extreme events that are captured as extremes in the reanalysis, and you can see that about half of these extreme events are captured and about half are missed by the reanalysis. But if you focus just on the strongest few observed events, then for most of them, they are captured as extremes in the reanalysis. And so that's good, because if we're, for our application in structural engineering, they're most interested in the strongest winds that have the most potential, for damaging buildings or something like that. It seems like the reanalysis is able to pick up on those events. And so that's good. We can continue to focus in on it. So then looking at this high resolution eCOA product that I mentioned, this has a spatial resolution of about 9 kilometers versus ERA 5's 30 kilometers. And so we wanted to know if maybe this high resolution product was doing a better job at capturing the extremes. It is available for a much shorter time period, only 2016 to present versus ERA 5 going back to 1979. But you can see it captures about a pretty similar proportion of the observed extremes over that period. So it doesn't really capture more extremes, but what it does do is it has a much lower wind speed bias. So it's capturing, it's simulating some higher wind speeds. Oh, whoops, I keep advancing by mistake. That's my bad. It's simulating some higher wind speeds, reducing this low wind speed bias that ERA 5 has, but isn't really doing better at capturing the observed extreme wind events. So we are wondering, is there maybe something different between these sort of captured and not captured observed wind extremes? And so what we wanted to do to look at this was examine the spatial scale of these extreme wind events. So the way that we quantify this spatial scale is using a decorrelation length scale. So what this is you draw a, so you pick the grid cell in this high resolution operational analysis product, the grid cell nearest to some station where we're looking at the extreme winds. You calculate the correlation between it and all the surrounding grid cells. You draw the contour where that correlation equals 0.9, and then calculate the average distance from the point to the contour. So you can see the example here of the red dashed line is the 0.9 correlation contour for the captured extremes at the station. Man, I keep advancing, I'm so sorry. Whereas the green one is for the not captured events. And so you can see it looks here that these not captured events may be characterized by some smaller scale spatial variability than the events that are the analysis is able to pick up as extremes. And so I showed an example here for one single station in Toronto, but I repeated this for a number of different observation stations across Canada. And you can see pretty consistently that the warm colored bars, which are for the not captured events, show a smaller scale spatial variability than the cold colored ones, which are the captured events. And so it may mean that the reason that the reanalysis are missing some of these extreme wind events is simply because they have spatial scale variability that might be too small for it to fully be picking up. Great. So now that we've established that ERA 5 is able to capture a good number of the strongest observed wind speeds as extremes in its own wind speed data set, despite its own bias, what we wanted to do is then look at the larger scales to see what sort of patterns might be showing up during these extreme events that we think that a climate model might be able to simulate well. So I've shown here some composites of the sea level pressure in ERA 5 with the climatology and the zonal mean removed to help tease out this wave train pattern that you can see here. I've stratified my analysis by the wind direction and like the local wind direction at the weather station where we're observing these extremes to try to see if there's some sort of different patterns that pick up depending on the wind direction. And that is sort of what we see. The percentages in the subplot titles basically show the percentage of the extreme events with that given wind direction. So for Toronto, we see there's very few southeasterly events, and most of the wind events are either, well, most of them are westerly, either northwesterly or southwesterly, but there's a good number of northeasterly events too. So one thing to note is if you sort of align yourself at the red dot, which is the location of Toronto, and put the minimum of the sea level pressure on your left, then you'll be looking in the direction of the geostrophic wind. And for most of the cases, you'll see that excuse me, I'm so sorry, I keep advancing the slide, that the wind direction is approximately consistent with the direction of the geostrophic wind. That is not the case though for these northeasterly extreme wind events. And so for those, they must have some strong ageostrophic circulation. In particular, it looks like the wind is pointing toward the minimum of the sea level pressure. So we expect that maybe the acylobaric component of the ageostrophic wind would be important, but that's something that I haven't quite looked into yet. I thought I would just sort of mention it quickly. Looking up into the free troposphere, we decided to produce composites of the winds at 300 hectopascals, where we'd expect the strength of the jet stream to be near its strongest. And what we see for these extreme wind events in Toronto is a jet streak pattern. So what that is you'll see that there's sort of an enhancement of the jet stream wind speeds in some region near the city, right in the trough of a wave. And so from the literature in meteorology, we know that these jet streaks can be associated with stormy weather, and in particular in two sort of quadrants of the jet streak. So the region is called the right entrance region, which is to the right of the region where the wind speeds are accelerating. I think it's advancing on its own, I'm so sorry. And in the left exit region, which is to the left of where the wind speed is decelerating. And so for most of these cases, especially the westerly ones, you see that the city is located right in the left exit region. For the northeasterlies, it's in the in the right entrance region. And so, yeah, that's exactly where we'd expect some severe stormy weather to be occurring. So I didn't show it because I don't quite have enough time, but there's a pattern of convergence and divergence in the upper level winds that takes place here. And so that can lead to upward and downward motion, which contribute to cyclogenesis and that sort of sea level pressure minimum pattern that we saw before. And so that is telling us that there are these links between the upper and lower troposphere for the dynamics that are driving these wind extremes. So the next thing I wanted to look at were these same composite patterns, but for extreme wind events in the CESM-1 large ensemble, and compare those patterns to ERA 5. So I selected the extremes here by calculating the 90th percentile of the wind speed distribution and using all the ensemble members, and then picking events in each individual ensemble member with wind speed above that threshold. And so you can see at a glance that both the upper and the lower level fields look almost identical to what we just saw for the ERA 5 reanalysis. There may be some slight differences. For example, look at the northeasterly events in the sea level pressure. The sort of high-low pressure dipole pattern is a bit more north-south oriented, where it was kind of tilted before, and I'll show that again later. And there's also a difference in the distribution of the local wind direction. And so, for example, there's too many southeasterly wind events in Toronto. And so since Lake Ontario is just right to the southeast of Toronto, we think that might have something to do with different representation of the Great Lakes and the lower boundary conditions. All right, so I'm running late on time, so I'll try to speed up a little bit. The next thing we looked at were these same composites for extreme winds in a variable resolution CESM simulation that we performed. So this was set up by a postdoc in my group for a different study, but we thought we'd want to use the data and results for this as well, since we just had it available. So this is a time slice simulation of just the atmosphere and land model with prescribed SSTs that are just the same for each year in the simulation, and year 2000 forcing. So it's the F2000 Climo C5 comp set, just with this custom refined grid where the region of refinement is right over Southern Ontario. So the resolution refining from approximately 1 degree over most of the globe down to about 7 kilometers right over Southern Ontario and near the greater Toronto area. So the results that I'll show are just based off of 10 years of this time slice simulation, but I've recently completed 20 years. And so I'll update the results soon once I've just been able to have a chance to process that. But still, we can see that for these sea level pressure and upper level wind speed patterns, there's pretty good agreement with what we saw in ERA 5, perhaps even a little bit better than we saw in the CSM large ensemble. So I wanted to focus in on these northeasterly extreme wind events. And so you can see I showed the composite here for ERA 5 again. So you can see this sort of tilted pattern in ERA 5 that we also see in the composite from VRCESM, where it was a little bit different in the CSM large ensemble. So we think that having this refined resolution is even helping us, improve the synoptic structures during these extreme wind events. Similarly, at upper levels in the jet streak winds, there's stronger, jet streak winds in the VR model than we saw from the large ensemble. It's actually even a bit stronger than we saw in ERA 5. So I'm not sure exactly what the reason for that is, but I think it's good that we're sort of picking up, stronger enhancements during the extremes in the VR model than we saw in the large ensemble. So that's encouraging. The other thing is it improves a little bit the distribution of the direction of these extreme wind events, the wind direction. So you can see the large ensemble really overestimated the number of southeasterly events, whereas the VR model gets it a little bit better. Similarly, it had a few too many sort of southwesterly events, and the VR model agrees a little bit better with ERA 5. So that may also have to do with its, improved representation of the sort of local topography that might be dictating the preferred directions from which these extreme wind speeds come from. Right, so just in summary, I'm a long time, so I won't read through all of it, but basically we found that AIR5 does a pretty good job of capturing these, observed extreme wind events, and then we've used it to produce these composites to try to identify some of the large scale drivers of these extremes. And then when we look during extremes in both the CSM large ensemble as well as a regionally refined version of CESM, we see really similar structures. And that gives us some confidence that these models may be capturing the important dynamics that drive these local extreme winds. And that sort of motivates us to look into this further, to try to see what we can use what we've learned to learn something about the climate change projections for extreme winds. So I showed this plot of the distribution of wind speeds now, putting the 2070s results from the CSM large ensemble. So you can see that it projects maybe some slight decreases in the mean winds, but of course this is something I haven't looked into much yet. So I just wanted to tease that for the work that I'll do going forward.
Great. Thank you, Michael. It looks like we have already one question, hand raised from Colin. Colin, did you want to ask your question?
Yeah, so I just wanted to say, so nice talk. The jet bias, where the jet increases in the variable resolution simulations, is an intriguing finding. It's not really consistent with a lot of stuff we've seen, so we should probably chat a little bit offline. But my question was regarding these kind of patterns, so like what you have on the left side right there. So it seems like the way you've been analyzing this is you take the wind at somewhere in Toronto, and then you kind of like break it down into quadrant and then composite these patterns.
Yes.
My question is, have you thought about going the opposite direction, which is kind of using AIR5 to define these patterns and then seeing how the patterns themselves are represented in the model? So kind of ignoring the wind for a second, but then seeing like, oh, well, maybe part of these errors that I'm seeing in this rightmost are not because of the kind of like the alignment or things like that. It's just because the model is not capturing the patterns. I was curious on your thoughts on that.
Interesting. I hadn't thought about doing that. There is some work I've been thinking of doing of trying to reverse it, just still with the AIR5, the observations of trying to, see if we can go the other way instead of using the wind as a guider, using the patterns as a guider to try to identify the wind speeds. That's something I haven't really gotten into yet. But what you said is really interesting, and that's something I'll definitely think about doing. Yeah, like I hadn't thought about that. I'd still been using the sort of winds in CSM to then identify the patterns and check the agreement, but going the other way would be really, really interesting to do. So thanks, that's a great idea.
Cool. Yeah, and I was actually pleasantly surprised at how well the winds in CESM look. So yeah, nice talk.
Thank you.
Okay, if there are no other questions specifically for Michael, let's open it up. So we have 10 minutes here for a bit of a broad discussion before we get into the next session, which is on dynamical cores and physics dynamics coupling. So I want to maybe start the conversation with some of the comments that are going on within the chat. So I think there was a question at one point, and I think it looks like Levi maybe responded to it, but it's from Andrew about whether you could use RCE to tune the model, for example, low-level clouds. And I don't know, maybe Levi, if you wanted to take a minute. I think you responded, but in case people aren't looking at the chat, maybe you want to take a second to elaborate on that response.
Yeah, basically the short answer is that it would not be a good idea to just tune some parameterizations using RCE and then think that they're going to work for the global model. I think all of you understand that better than I do. But I think we can still learn something interesting about how the clouds in, say, for example, the relationship between club parameter settings and low-level clouds. We can test that out in RCE. The fact that RCE looks like the parent models in terms of which model has more or less low-level clouds is encouraging in that regard. But then, of course, obviously, we would have to use those same parameter settings in club in like an AMIP or a historical run to see what happens. I suspect that probably the exact settings we used in club to change things probably have already been tested in the AMIP or historical run. And I suspect they would degrade the simulations in other places, but it'd be worth looking into anyways. But I just think it's more like the first step of using those kinds of parameter changes in RCE could be hopefully useful in mechanistic type studies or something like that.
Yeah. Maybe before Andrew, I see you raised your hand, so I'll let you go in a second. Before that, I wanted to add maybe a part to that, which is I think that if there are differences in low-level clouds, just an example, and maybe it's not the best example for RCE, but we do see those similar differences in the realistic simulations that Levi showed. But also, if you look in the deep tropics, for example, over the warm pool, there are differences in low clouds between CAM 5 and CAM 6, and of course, in any study in which you're trying to understand which one of those might be more realistic, then the RCE, I think, as Levi was suggesting, could be really helpful in understanding what is the impact of these different parameter choices, to at least understanding a little bit of that. But then advantage of any idealized simulation is often the fact that you can get robust differences in much shorter simulations than are typically required sometimes for long-term coupled simulations. But I'll let you to add some thoughts, Andrew.
Yeah, I think I would agree with both what Levi and Kevin you just said. I think that's a good approach. One thing to note that might help, and if you wanted to dive into it, Levi, is true to Idahammer talked about this perturbed parameter ensemble that we did with 250 different runs. We modified most of these club parameters. Basically anything Vince said we could modify, we modified. And we're using some emulators now. And if you're looking at targeted things like how does it change the low clouds, how does it change the forcing, how does it change the liquid water path in particular regions, they're full 3D runs. And we're developing technologies to use emulators to ask these questions. So we can probably use some of that mapping, and actually, in other words, you don't have to run the model. We've already done it. So there may be some opportunities to take some of the questions that you can ask in the RCE and apply them to the low cloud regions of a full, F case, basically.
Yeah, that sounds super interesting.
So anyway, all that output's going to be available on our systems and for people to use. And we're getting more experience with these emulators. We're going to be using this stuff to actually tune up the next model to understand the sensitivity. So looking in this particular question about a transfer function, I think you could use this data set to kind of approach that without having to run the full model a whole bunch of times, because we've already done it.
Yeah, good point. That sounds interesting. Thank you.
Colin, you had your hand raised. Did you want to?
Yeah, it's kind of just a quick follow-up, but one of the things that I know we've talked about, maybe not so much during this AMWG, but previous meetings, has been kind of leveraging things like large eddy simulations to improve the models as well. And I know there's a pretty big large eddy, or at least super high res component to RCE MIP. I was wondering if either you or Levi could speak to the potential of, would RCE, these RCE configurations, would they be a potential bridge maybe between LES and the model? So kind of the way we do it right now is you run LES, and then we run either SCAM or the full model. But I'm wondering if maybe filling some of that gap in with the idealized configurations could be an option.
I think it's a good idea, but my impression from the initial RCE MIP results that people have looked at is that definitely the cloud resolving models, which used 3 kilometers, but I think this is also true of the LES models, which are higher resolution, that we were surprised at how little convergence there was, that the results were still, the cloud resolving models didn't look more similar to each other compared to the parameterized global models. And that's kind of amazing. There's obvious advantages to the cloud resolving models, even if they don't all look the same. But I think that perhaps the LES models looked a little bit better in that regard, but I don't think it was a dramatic difference. And so I suspect you'd have to do it on a case-by-case basis of, why do you trust the LES model more? And of course, there are reasons to trust it more. And it seems like it's not as obvious as people hoped it would be that those could be a bridge, because they have such a huge variety of responses in mean climate states.
Good job security for us, I guess. So thanks.
Yeah.
Maybe on a related topic, I see that, semi-related. I see that Brian Medeiros wrote in the chat that this is kind of broad, and so maybe it's a good for the broader discussion later in the day, but we can bring it up here too, is that I think we saw some examples of simulations that others have done that aren't necessarily CMIP official simulations, but are inner comparisons. And Brian's asking if there's any mechanism on deciding for how to allocate computational resources for these more kind of informal CMIP or let's call them non-CMIP endorsed MIPS, but they're still MIPS all in the same. In particular, because I think there are a lot of requests that go around for NCAR groups to be involved in different modeling comparisons, but it's not clear where to find the computer time. And I think, of course, this is a broader question related to the fact that there are a lot of aspects of using model hierarchies. And one of the advantages of CESM and CAM over a lot of our peer modeling centers is the fact that we do have this simpler models initiative that has this pretty broad range of configurations of the model. And that can be used by the university community, but that also means that there's need for computational time for it. So I don't know if anybody has any thoughts about that, or maybe just keep it in the back of your mind. I think it'll be a good discussion point for our kind of full discussion at the end as well. If there are no quick thoughts, I think, Michael, there is one, or at least a question, or I guess it's maybe a clarification. I'm reading it as I'm talking, so I'm not too invested, but I think Colin, you have
some thoughts on the MIP topic before we go on.
Oh, I see that. Yeah. Okay. Go ahead.
Oh, okay. I didn't want to derail the discussion. I just, there is a proposal process for the AMWG allocations. And in the past, CISL has been less, I guess, I'm going to say anal about matching the runs that are actually done with what's in the proposal. So that gave us, I guess, some flexibility to, just let people do things. They're becoming a little more stringent about trying to match the AMWG CSM allocation proposals with the runs that are actually done. So that makes it a little less possible to just kind of hand out computer time informally.
Yeah. Brian, did you want to add something before I turn it back to Andrew, since you kind of started the conversation?
Yeah, just that is exactly kind of the issue that I'm concerned about, because a lot of these informal MIPS arise relatively organically in small groups, and they're not long-term projects, so it's hard to write them into proposals because they don't have that kind of lead time. We don't have a year to wait around for them, because they come up and they're like, oh, can you do these runs in the next few months? We're writing a paper right now. Yeah. So I wonder if we need some process to be able to get that more ad hoc computer time.
Yeah, I mean, there is the CSL calls, but they are typically for, massive multi-million CPU hour projects, typically using high resolution configurations. But yeah, I agree. I think there's got to be some other way of enabling this.
I think the other side of it would be the fact that there is, of course, small requests that you can put in as member institutions, or particularly, obviously, if you have NSF funding. But some of these things are so, I think, as Brian is suggesting, might bubble up at such a kind of grassroots effort that they might not have proposals yet, or it might not be small. It might be small, but still not small enough to be a small allocation. And so I think there's almost some off-cycle opportunities for non-NSF funded, for example, university researchers to potentially kind of work with NCAR to get some of these kind of MIPS or something in. Or I don't even know if we want to call it. We have MIPS on top of MIPS nowadays. So Andrew, did you want to add something?
Yeah, I was just going to add a plus and a minus here. So the plus is that on the annual timescale, we do typically write we typically have an AMWG atmospheric allocation, and they look very favorably on community projects. So if it's something that's going to take a couple million core hours or many million core hours, and it is actually a community project that people are interested in, it's not a zero-sum game, and we can get time for that. But that's sort of an annual timescale. On the minus side, I would, and having been asked a lot and continually asked to do runs for people, using major amounts of computer time because somebody's writing a paper is maybe not necessarily a community project. If you can't wait a couple of months or a year, maybe we shouldn't be using our community allocation for model development or for production to do that. So just to think about, I think the small request things are useful. There is a gray area. I think if it's scientifically interesting enough, we do it, basically. But if it's a huge lift, if it is a good community project and there are people behind it, and then it should have some legs, even if it's not an official MIP. I forget, Julio, exactly what the time scale of that is, but usually the allocations are done in the fall. And we can certainly write things into there that I think it's not a zero-sum game, and we can get additional time if there is community interest in something. So that's kind of a plus and minus.
The big the AMWG allocations are 2 years. They're every 2 years, and then.
But they get adjusted every year, pretty much.
Well.
Anyway.
All right.
Yeah, I'll say this is a good conversation, because I think maybe we, as a working group, if we gave some feedback to CESL, I think, or started at that, I think it could be beneficial. And so I just want to make sure, Michael, that there was a comment referring back to one of your talks in the discussion you had with Colin in the chat. So be sure to check that. There's already some discussion continuing, but I want to move on to the next session of the morning, which is about dynamical cores and physics dynamics coupling. So first up, we have Peter Lorentzen, who's going to kind of give us a current status of CAM dynamical cores and vertical resolution. So.
Alrighty, can you hear me?
We can hear you, and we can see the full screen, so you are good to go.
Alrighty, I have been asked to give an update on dynamical cores and vertical resolution. I think Julio and Rich in particular have been talking quite a bit about the new vertical resolution, so I won't talk about that and instead talk about enthalpy flux plans, as that impacts physics and physics dynamics coupling quite extensively. Let's start with dynamical cores. Here's a slide from AMWG 2016 in the red box here. And back then I was talking about moving away from the finite volume dynamical core and these other Eulerian SLD dynamical cores towards what I would call these next generation dynamical cores that are being actively developed. We have spectral elements in there, we have MPAS, and we also have FE3 in the mix. As Julio alluded to, the software engineering group is giving us the feedback that having 1, 2, 3, 4, 5, 6 dynamical cores in CAM is becoming more and more of a heavy lift. So I'd like to initiate the discussion with the community if we can bring this number down. Since 2016, we have made progress. We have removed the SLD dynamical core. Next on the list could be the Eulerian dynamical core. However, that is easier said than done. One issue is it's used in the SCAM setup, the single column setup for doing vertical advection. That's simply just grandfathered in there from a numerical methods point of view or consistency point of view. It's not very consistent to use a vertical advection from a different dynamical core if you're running, say, finite volume. So we got to change that. Also, the Eulerian dynamical core is very popular among dynamicists, and it's also ultra fast and small machines. So we would need to provide some kind of alternative that can make that community happy without Eulerian. And at some point, we're probably also going to be thinking about finite volume. However, since finite volume was used for the 1 degree CSM2 IPCC simulations. We'll need that as a reference for a while. And also it's used for low resolution applications such as paleo and low res Wacom applications. So we need to provide an alternative before even beginning the discussion of a decommissioning of finite volume. In terms of the next generation dynamical cores, here's a status report of where they're standing with respect to the CAM7 1-degree applications with the new model TUP that has implications for the dynamical core. Spectral elements fully functional. We're actively using it now. MPAS, we fixed some physics dynamics coupling issue that appeared at very high horizontal resolution. We're very close to have the fontogenesis functions ready. They're being computed by the DICOR and then passed to physics. That's needed for the parameterizations that we used when using 80 kilometer and above model TUPs. And then we need to set up MPAS for this new vertical resolution so that things run out of the box. There's lots of other stuff going on here that's going to be talked about later on in the SEMA and Earthwork talks about what's going like lots of stuff going on with MPAS at high resolution and high TUP. FE3, we're in the process of upgrading to the new GFDL code base. We need to implement the fontogenesis function and again setting up so that we out of the box can run FE3 with this vertical resolution. So as Julio mentioned, we are at the moment putting all our effort into developing CAM7 with spectral elements. However, we want all these other DICORs to be ready in case we want to swap out the DICOR, but also in particular to allow the community to do dynamical core science with these different dynamical cores, as CESM, to my knowledge, is the only coupled modeling system that has access to more than one state-of-the-art dynamical core. So that's all I have on the dynamical core side. I'm sure we'll discuss more later. Now to the enthalpy flux plans. Let's first remind ourselves why are we talking about this? Why is this an important thing to talk about in relation to CSM3? Well, first of all, we're going to use the MOM6 ocean model, and that model's formulation requires explicit specification of the heat flux associated with water leaving the ocean or entering the ocean. These are also known as enthalpy fluxes. So whether we want it or not, the ocean does want enthalpy fluxes. Second, the atmosphere does not currently have explicit enthalpy fluxes in it. So that means that effectively that the global energy fixer in CAM takes care of these fluxes. So whether they are going in and out of the atmosphere, currently all the energy stays in the atmosphere and is fixed via a global temperature increment. And a year ago, I gave a talk entirely about what all these different terms look like in real world climate simulation. You may then ask, why don't you just add these terms and then we're done? They're not really that complicated. It's just a specific heat times a temperature times a water flux, and then we're done. Well, if you were to do that and do nothing else, then you would introduce energetic and thermodynamic inconsistencies in the coupled system. So we have to be really careful about how to proceed here. Then you may ask, well, what should we do? Well, if you want energetic consistency, you have to show me what is the energy equation that we're using. And answering that question in a general sense is incredibly hard. So I've teamed up with a large number of researchers to answer this question, and we've written our ideas up in this paper here that's always a week away from being submitted. But I would like to highlight that in this manuscript here, there is an in-depth discussion about this CLOP-CAM thermodynamic consistency issue that Adam Harrington was talking about in his talk. So the energy equation, if we make a bunch of assumptions, we can derive. So in the interest of time, I won't go through all of the assumptions. They're listed up here. And if you make those assumptions, then you can show that the time change of the global integral over the entire atmosphere of kinetic, potential, and enthalpy here for dry air. This term here is for all the water species in the atmosphere. When you have water species that do phase transformations, you also automatically have these latent heat terms. So the time change of the global integral of all of this should equal the flux of these quantities in and out of the atmosphere. So F here is the net flux of water species L. And then you have the kinetic, potential, and enthalpy terms here, latent heat terms. And then I just put all the turbulent or sensible heat, flux, and radiation to this term here, which are not important for the current discussion. CAM then makes further assumptions to this equation here. First of all, we assume that only water vapor is in this sum here. Secondly, we assume that the specific heat of all forms of water is that of dry air. That's equivalent to saying that we're using constant latent heats. And then we get rid of all of these terms here. And this term, the CPT term here, that is the enthalpy term that NOM 6 really, really wants us to include in our model. And then last but not least, doing physics updates, we hold total water fixed, which is equivalent to keeping the mixing ratios of all water here fixed during our physics parameterizations. And then at the very end, we do update these water variables, and the energy change associated with that, we fold into a global energy fixer. So our plans for incorporating enthalpy fluxes in the atmosphere in a consistent way is the following. And it's basically going to be undoing as many as these assumptions here that I just went through one by one. So the first one would be including all forms of water in this term here. It has a relatively small energy budget implication and is in theory relatively straightforward to do. So I think that should be our first step. The next one is harder, but necessary. So we want to get rid of using one specific heat for everything. I would like to note here that FE3 and SE already use variable latent heat in their formulation. So in other words, they use the more correct latent heat or specific heat for the different water species in the atmosphere. So the dicores already have it. What's needed on the physics side? Well, first of all, the thermodynamic variable that's used to update the state in CAM, for those of you who know the code, is %S, needs to be updated to use variable latent heats. I think I know how to do that. But what might be a little harder is that if parameterizations make the assumptions of using constant latent heats, then we need to change that. Also, I want to mention NOM 6 enthalpy fluxes. They do not use the specific heat of dry air for the enthalpy fluxes. They use the ones appropriate for whatever water species moving in and out. So therefore, we need that in the atmosphere as well. The third part is now incorporating this term into the model. And of these three terms here, the kinetic, potential, and enthalpy terms, this one here is where over 95% of the energy imbalances are. However, there are some caveats here. We need to specify a temperature at which water enters the atmosphere or leaves the atmosphere. In this equation here, I just assume that it's the same temperature regardless. One can undo that assumption relatively easily, but it just does make this equation a little bit more complicated. In terms of evaporation, I think it's pretty straightforward. We should probably use the temperature of the surface. So over ocean, that would be the SST. For precipitation, it's more complicated because precipitation is usually formed higher up in the atmosphere. Let's say it's formed here at the base of a big cloud, and then it starts to become falling precipitation. So that means it would have a temperature different than the temperature at the surface when it was formed. If you were to use that temperature down here, you're effectively neglecting anything that happens to this rain droplet as it leaves the cloud and hits the surface. And we know there is stuff going, it is interacting with its environment. One thing that is happening is there's a frictional heating of falling precipitation that will heat up the droplet as it falls. Just as a little side note, the barocentric velocity framework can actually naturally incorporate this effect. And if you want to see the full details, see this manuscript here. You could also use the temperature at the lowest model level, in which case you assume that the droplet would exactly have heated from whatever temperature it had below the cloud base and then when it hits the surface. So long story short, there's some ambiguity here to specify this temperature. But I would argue, regardless of what we do, this could lead to a major improvement in the energy equation. So this is just a diagnostic to look at what these different terms look like that I showed last year, but here's a little reminder. This plot here on the left-hand side, that's basically the effect of updating water vapor after we're done with all the physics parameterizations. So you see you have rather large values here in the evaporation zones and in the Pacific, like 20 watts per meter squared. And then even also in heavy precipitation areas with a different sign. And that's what we all put into the global energy fixer. If you compute this term here, which has the enthalpy term, these guys here are pretty small, you get a plot that looks almost exactly the same as this plot on the left-hand side, at least regionally. So if we were to include this flux in CAM, then our residual will look like this. So the average hasn't improved much, but regionally you get massive improvements. So instead of having 20 watts per meter squared in this evaporation, so we are now down to like minus 0.5 watts per meter squared. And this is using just the temperature at the lowest model level. So even if that has some uncertainty associated with it, it does decrease the energy budget imbalances, maybe not entirely for the right reason, but hopefully mostly for the right reasons. With that, I'll take questions.
Awesome, thank you, Peter. Are there any questions from the group? Maybe I'll ask a really quick question, Peter, which is just based upon, what would be the timeline for including all of these things and kind of the, is this something that you anticipate could be available for CAM 7 or?
Yeah, so I did mention this, there's a fix that Gustavo told about in the ocean modeling working group meeting that's been put into the coupler, meaning that there's a fix that takes care of this, so we can proceed with developing CESM-3 in the short term. But we're definitely planning to try and get this in for CAM 7. But obviously the changes are pretty extensive, so you're probably not going to see anything for at least a year.
Okay. And I'm just curious if you've started to look at just what if these changes have any unintended consequences, if you look at other fields or circulation or anything.
Yeah, so all we have been able to do is just diagnosing the terms. So yeah, changing to variable latent heats, we'll see what that does. So.
Okay, I think there's been one question in the chat, which maybe you can get to after, but I'll let Thomas raise his hand. So Thomas, you can ask a question and then we're going to move on and come back to everything in the group discussion. So.
Hey, thanks a lot, Kevin. Peter, just to mention the fact that in OSM we are applying that sensible heat flux associated with a precipitation flux already. So those the tendencies that you showed in the third panel on the right-hand side of the last figure in your plot is actually a tendency that is applied in OSM as well. And the surprise there is that the impact is actually not very large at all. Now there are many open questions on how you apply that heat, and ultimately we take the global integral and fold it back into the fixer again, because the ocean cannot take, as you described very well in your talk, the ocean cannot accept that local heat flux directly without violating the couplet model's energy conservation. So ultimately, everything gets back into the global fixer. But the local tendencies are applied for a temperature in OSM, and although there might be dependence on how that is done, we don't see a very large impact actually in the simulations. So that is relatively good news in the sense that it means it doesn't completely throw off other model tunings, I think, in the atmospheric component.
Yeah, thanks for reminding me of that. The difference that's going to happen here, I think that you use the specific heat of dry air, no? And we're going to use that of whatever the water species is. So for precipitation, the flux is going to be like 4 times larger than that of dry air. So it might give it a little bit more of an effect, but
yeah,
I think you're correct that is good news that everything is not completely going haywire.
Okay, well, I think we should move on. So next up will be Christian Jovanowski, who's going to talk about the numerical characteristics of one of the die cores, the FV3 die core that's in CAM. So take it away. And we can see everything well, yeah?
Yeah, thanks a lot for having this opportunity. And I kind of follow on, Peter gave an introduction to kind of the suite or portfolio of die cores that we have in CSM or CAM, and I dive into FV3. And Owen Huge, who's my co-author, also Peter, Owen will dive into SE actually in a minute. Okay. So I guess the key question and focus of the talk is, what are the impacts of the FV3 numerical design on the fluid flow? And you can answer this question by looking at the explicit damping characteristics, for example, the external mode damping, divergence damping. Then there is implicit numerical damping in the horizontal, also in the vertical, I should say, but I'm not focusing on that. There's a virtual remap algorithm and sponge layer diffusion, for example, Rayleigh friction, and many other things that I can't go into. And I know not everybody in this community is a DICO person, so I will guide you very briefly through these design concepts. Okay, so before we look into the specifics, let me give you an overview how this is designed, the evaluation techniques. We are here using the simpler models framework that was mentioned already, available in CSM 2.1, and here 2.2 is now extending or has extended the functionality. Also, the DCMIP project, the Dynamical Model Intercomparison project, has contributed to these evaluation techniques quite a bit, and you will see a few of these test cases. We are focusing on hydrostatic large modes. There's no complex physics interactions, either it's dry or Kessler physics, which is kind of a warm brain scheme. And I at times put the FV3 results into context and give you some insights into the other models. And the test cases here are the so-called acid test, which is just a mountain and no flow, and nothing should happen. And we will see whether this is true. There is a moist baroclinic wave we tried in DCMIP 2016, and many of you might know the Hertz-Rares test, which is a temperature relaxation and Rayleigh friction. The models that we are looking at, well, they come from various code bases. So this is not just the latest and greatest CAM development, which we also use. So at times I give you pointers where these code bases are coming from. We also, as I mentioned, we use code base from just a few weeks ago from January, especially for FV3. And here you see, for those who are not familiar with kind of the jargon, FV3, that's the finite volume cubed sphere model from NOAA GFDL, now in CAM. And here are some of the resolutions spanning from like 400 to 50 kilometers. We have the spectral element model SE, with 2 resolutions here highlighted, and these are the acronyms. We have the old-fashioned finite volume like long grid, here used with 50 kilometers, and MPAS with 60 kilometers or 120 is also available. So Given you, maybe let's start diving into some of the test cases. First one we looked at is actually the Bauer Clinic Wave test case, but this is from DCMIT 2016 by Ulrich and all, but we augmented it and we put in some mountains, and you see the mountain shape here. And then we run this, and you see this is a surface pressure. You see actually quite some gravity wave motions. Of course, the Bauer Clinic Wave also develops here, triggered by the mountains. You also see precipitation, temperature fronts, and the overall water column. And now, as this is a 10-day simulation, you kind of see the high and low pressure systems evolving. And the trigger of these Bauer Clinic Waves, these were the two mountain ranges. We call it the Ridge Mountain. Everything is analytic, so this is easy to use with all configurations of CAM. You can just run it for 10 days, and after 5 you get actually almost kind of the peak evolution here over the second ridge. This was an animation from CAM SE, and I highlighted up front, I highlighted this gravity wave interaction, and let me actually show you this a little better. The gravity wave interaction, or high speed, I should say, high speed gravity wave, appears in all 4 dicores that CAM has. Here we see an example here of the omega 850 field at like half a day and day 2. And this wave travels all around the globe within a day and a half. So it's very high speed, and Owen will actually focus in his next talk on this. This is from FV3, 2 different configurations, which not that relevant right now, but we see actually, and this is good news, this gravity wave, it's actually an external inertial gravity wave, external mode, is damped actually quite heavily after 2 days. So there's an indication here that it's no longer that severe. Note though, here in the corner, I have the same figure from SE at day 2, and there is no indication of any damping in SE. So this was kind of an intriguing finding, and we were diving into this a little bit. So how can you dive into that? Well, and the question is there an initial imbalance caused by the topography in this Bauer Clinic Wave? The answer is yes. And then the question is, how big is the imbalance? And you can ask this question with another test, which is the acid test. And here you see now a vertical cross-section. This is a longitude vertical cross-section at the equator of the U field at day 4. As a test, nothing happens. You have no flow. You have a stratification, the temperature, and a mountain. And the analytic solution is no flow. But of course, a mountain creates some disturbances in the flow field, and the numerics pick it up. And here you have it. So these are the errors from FE3, and I should note they are very low. Just as a comparison, SE, this is here to the side, has errors that are 20 times bigger than FE3. We had actually very engaged discussions even last week with Peter about that. Note that the home model implemented in the DOE version of E3SM does not have these big errors. The errors look alike or resemble FE3. So there's something going on in SE. And maybe it's actually then the trigger for these persistent gravity waves that I just showed you. So this was kind of an intriguing find, but kind of not the end of the story. Of course, FE3 has a high-speed gravity wave, so you can ask the question, can this be damped in any way? Although it's not that severe, the answer is currently not. Why not? Well, the damping mechanism for such a gravity wave would be the external mode damper. This is actually a switch-on option for those who haven't seen an external mode damper. It's basically the integrated version of the divergence, a horizontal divergence, and you integrate this vertically. There's a coefficient, and that then becomes a damping coefficient or damping momentum forcing. This is a switch-on option. And then I gave it a try, and here you kind of see some of the values. There's no damping in this one, but then I'm increasing the strength. And interestingly, there was no safe value of the external mode damping. All values, when I switched them on, actually led to the grid imprinting and numerical noise around the cube sphere corner points. So currently, there's something going on with the external mode damping, so not an option to use, which was an interesting find in this context. Well, you can ask more questions. For example, what is the impact of implicit numerical diffusion? Yeah, external mode damping is explicit diffusion, but how about, you change the characteristics of the advection scheme, and this can be done via nameless changes. For those who are familiar with that, this is done via limiters in the finite volume scheme or monotonicity constraints. Here are some of the references or numbers. This is coming here from Lucas Harris from a GFDL training session. There are many options available, and also you can damp various terms differently. For example, vorticity can be damped differently than temperature. And here are kind of the acronyms, and 5 and 10. 6 is also in the mix of being popular, but these are kind of choices we see quite often, either at NOAA or at NCAR. And NCAR is 10 as a default. And now you can ask the question again, yeah, what's the impact of this implicit numerical diffusion in FA3 in a baroclinic wave here with the two ridges, varying, as you see now, these diffusion characteristics of the implicit advection. And, at first looks alike, but no, it's not. Just take a note here, the minimum surface pressure after 5 days is 10 hectopascal different between these two. And you can see also, you see it here in the timeline, this is over 5 days. It's very different. The evolution, if you have a non-diffusive or highly non-diffusive scheme, this is 5, the evolution is so much quicker, the intensification than a more diffusive scheme. So it does matter. And it's actually 10 hectopascal difference, as I pointed out. That's a lot. Let's take a look how other models are doing. FA3 by itself, you can't really tell what's right or wrong. When you look at other models, here are now the other dicores, SE, FE, FE3, and MPAS at 50 kilometer resolution. You see actually that, and here's a timeline, the 5-day timeline. Interestingly now, SE, FE3, and MPAS are tracking each other very, very well. You see the kind of the overlay here in the bunch here. And it's actually FE3 with a more diffusive option, which is 6, that is an outlier here. Also FE, the regular FE is more diffusive, but that's an interesting find. So it does matter. And actually the least diffusive option matches other models the best. Well, there are more stories to tell in the implicit damping. And one is the divergence damping. And this is, again, something that it's in depth for those dichrome modelers. You have seen it here is actually the mechanism. And you see this is kind of denoting the divergence, higher order divergence. This Q then can be increased, for example, from 1 to 4, and this is kind of denoted here. So 2nd order, 4th order, 6th order, 8th order divergence damping, and it's becoming more scale selective. And again, you can assume a more scale selective scheme is less diffusive. In general, that's true, but you can overdo it. And I want to just highlight that in my findings, the 8th order divergence damping is actually not a good thing. You already see it here that it's very much not diffusing, and it's now allowing noise, and it's very dominant noise. You see it here. This is the 8th order divergence damping. Unfortunately, this is the NCAR default if you get it out of the box. So I really highly recommend to go to a lower order damping like the 6th or 4th order damping and the divergence damping, which really eliminates all this small scale noise. Okay, I only have a few more minutes. Let me kind of wrap up. Question number 6. What is the impact of a vertical remap algorithm FE3? Again, for those who have seen FE3, that's also true for SE and FE. The vertical advection is actually not explicit. It's done via interpolation and vertical remap. And again, FE3 is coming from Lucas Harris, is coming with many, many options, and you can change them depending on the variable. Especially temperature can be switched from, temperature remap from potential temperature to potential temperature. That is not a good thing, as we now see. So default is actually that the remaps temperature, and this is a Hertz-Rarus configuration with very high model top, like a Wacom configuration with 140 kilometers. If you switch this to the potential temperature remap, it's not a good thing. You see the striping here, you see a lot of temperature increases here near the model top. And turns out this is even a broken feature in the latest and greatest CAM development. So the model blows up with that option. So not something to recommend, but it's available in principle as an option. And last but not least, the There's also friction, rarely response friction available, which is a nameless option. This also needs to be used with care. If you just switch it on, it comes with something called local conservation of energy. Basically, friction lost momentum gets converted to heat in an effort to conserve total energy. That sounds good, but it's very questionable actually. And you see the effect of it here in kind of the upper domain of a Hertz-Raris configuration. If you switch on frictional heating, you get high temperatures in this region versus no frictional heating with the same model configuration. You get these low temperatures. Okay, summary and then a plea. So I just wanted to highlight kind of the complexities that are in FE3, highlight some of the bugs and problem areas that we still have in FE3. This really should provide dynamic core developers and stakeholders from GFDL and NCAR with more information and also suggestions how to improve FE3 even further. But okay, I stop with the plea, and I really would like NCAR and affiliated members to make MPAS community ready. What I mean by that, we heard from Julio that we want community evaluations of die cores. However, none of the things I showed today could be done with MPAS. Despite the recommendation that MPAS FE3, they should be supported options in the future. Standby options, basically. Why is that? And here I close. MPAS needs all these external tools for grid files, and unfortunately, these tools are not available to the community. And my plea is to make this happen and to really add full support for 240 resolution and all the tools that MPAS needs. And next time I'll probably talk about MPAS here. Thank you.
All right, thank you, Christian. Is there any quick questions or so? Let me scan the. So Thomas has two quick questions in the chat. Do you need enormous stencils to compute the high order diffusion operators to a given degree of precision?
No, you are repeatedly actually doing it. No, the stencil is only 2 or 3, so you don't extend the stencils. You're just repeating the operation a few times. So okay. Second order divergence then gets repeated twice, and now fourth order.
So I think Thomas is. He might have a second question, but we'll have to do it in the chat. So we're going to move on to the next speaker, if you don't mind. Stop. Yeah, the next speaker is. Going to continue on this discussion of the die core. So the next speaker is Owen Hughes, who's going to talk about the numerical characteristics within the SE die core. So, Owen, do you want to try sharing your screen?
Can you all hear me?
You can, yep.
Can you see my slides?
Yes, we can. And
okay.
The full screen looks good. Take it away.
Great. All right. So my name is Owen Hughes. I'm a senior undergraduate at the University of Michigan, working with Christiana. And today I'm going to talk about some very specific numerical characteristics of the spectral element dynamical core. It's going to touch a little bit on diffusion, but mostly on the impacts of sort of a lack of diffusion. So the overarching goals of this presentation are to talk about that gravity wave in the previous presentation that Christiana talked about, to investigate it a little bit further. Why does it show up so strongly in the SE die core? And for example, is it due to problems with discretization in the of the analytic initial state? What's causing it? What causes this wave to propagate? And how can we use this information to guide the configuration of the SE die core? Firstly, we saw in Christiana's presentation that there is this these two gravity waves triggered by topography, which then propagates quite rapidly around the surface of the Earth. Here, I've shown the finite volume Latent, FE3, MPAS this is a standalone and SE. And by far, when you get to about day 6, the gravity wave signal is still very well defined and well resolved in the SE dicore. So usually, if it were like a standard gravity wave, you would expect it to have a 3-dimensional extent and to have vertical structure that varies with time. But this wave it only decays in the vertical component and propagates purely horizontally. And indeed, when you increase the resolution, here I've shown nominal 1 degree and nominal ½ degree on the right. When you increase resolution, the propagation of this wave actually becomes more intense. The maximum amplitude is larger and remains that way for the duration of the simulation. In order to understand exactly why this is happening, I want to go to a more simple, for example, what Christiana mentioned about the acid test style simulation, which has topography, no base flow state, no rotation, and then I move the topography to the equator so that I don't have, so that essentially I want to be able to analyze the structure of this wave in as pure a form as possible. So this produces a radially symmetric wave, and the vertical structure is essentially just a decay in the decay. And I'm usually using omega here because the base state is 0 and it's pretty easy to visualize. So basically I want to, this is clearly an external mode and which is basically a form of gravity wave that is closer to an acoustic wave than what you usually think about. So this is what's called a Lamb wave, which is or an external mode. Those are two terms that don't always get associated with each other, but they are the same thing. And it's a horizontally propagating acoustic mode. So it doesn't have acoustic propagation in the vertical, doesn't cause time stepping problems there or model blow up, but it does propagate at the speed of sound. It's in hydrostatic balance, and it has the highest amplitude at the surface. So CFL conditions in dynamical cores are chosen to respect numerical instability that can result from this style of wave. And to sort of draw a parallel, Lamb waves and gravity are essentially equivalent. They propagate thermodynamically in the atmosphere, but they are equivalent to gravity waves in a shallow water model, if you look at them more detailed. In the real atmosphere, they only happen when something as extreme as, for example, a volcanic eruption happens. They're not especially common, and as a result, you would expect that a well-formed simulation, these would be relatively rarely generated in an ideal simulation, but they are physical, so you would expect them to propagate. So what I want to show here is exactly why one way of diagnosing that this is a Lamb wave, which is in the idealized topography only, no rotation, no flow, simple model run. You can look at the omega field at the equator and basically track the slope of the minimum pressure as it propagates. And what's shown here is simulations where the temperature of the atmosphere is isothermal from pole to equator and in the vertical. And as you increase from T equals 270 Kelvin to 305 to 350, this slope becomes steeper, which indicates that the speed of this wave is increasing with time, or is increasing with temperature. And from a pretty, like the simplest linearized wave analysis you can do, you can get the dispersion relation for the speed of sound, and using the isothermal conditions and the dry atmosphere, you can determine that the computed speed from the simulations matches very closely with the analytic speed. So if you are running into something that you think is an analytic mode is a external mode in a simulation, this is one way to diagnose that. Okay, now we get to some more specifics of the SE die-core. In particular, the spectral element die-core, it runs sort of parallel to the higher order methods modeling environment, HOME, which Christiana mentioned earlier, which is currently being developed as part of the E3SM model, which is the Department of Energy's Earth System model. And in this version of the SE die-core, there are 3 separate equation sets that have different, very different properties. There is the hydrostatic primitive equation, equation set PrEC-X. So this is the most similar to the SE die-core that's currently in CAM. There's the non-hydrostatic shell atmosphere equations with prognostic T. So this is the theta die-core. And this one is currently sort of backburnered, and what DOE seems to be particularly going forward with is the potential temperature variant of that die-core, which is theta L. And if you run this same acid test in the home configurations, you see that this external mode exists in all of them, has approximately the same magnitude, and propagates very similarly. So this indicates that, for one thing, the triggering of this wave is consistent through different prognostic variables, different diffusion schemes. This is relatively robust, and that the propagation of this wave, although not necessarily atmospherically relevant, is probably physical, which means that, okay, so if we have external modes, which are relatively small amplitude, propagate very quickly, and are, but what triggers them is almost never a physical process. How do you remove them? So Christiana mentioned earlier, FV3's attempt at implementing external mode damping. And just to remind you, this takes the horizontal divergence at, for example, a grid point, integrates from over all model levels. And basically, if you take an integral and another divergence operator of this, you find that it is a second order diffusion term acting on this vertically integrated divergence. And because Lamb waves have vertical structure that they are not going to, if you integrate them, they won't cancel out in the vertical, that this is a relatively selective way to remove external modes. However, the strength of this damping has to be calibrated for your grid resolution and your time step. So it's analogous to a CFL condition. And the last part of my talk, I implemented a rudimentary external mode damper in CAM SE to see if it affected the development of this wave. And this is a relatively rudimentary implementation that doesn't take advantage of some of the clever substepping that CAM SE is doing. And so the major results that I have are that it takes around 6 days or at least 3 days to really see a difference in the propagating wave with the external mode damper enabled. However, trying to put this KE coefficient, which determines essentially how strong the damping is, trying to put that higher caused numerical instability issues and grid point oscillations that cause model explosion. So there are probably cleverer ways to implement this that would be better at dealing with this kind of mode. But this is sort of part of a broader issue of, like Christiana mentioned earlier, diffusion in SE. When it's enabled, we see that essentially the error, this is another acid test where there is topography, no flow, so you'd expect to see essentially nothing. And when diffusion is enabled in the SE model, you when it's enabled in the SE model, error is orders of magnitude larger than any other model. However, when you remove diffusion, it immediately goes back to normal. So what you can see in these figures is that the error that's appearing is over the mountain when it's orders of magnitude larger than it should be. And it is not appearing in this Lamb-wave signature, which is what we're seeing on the right-hand side of this plot. And so I would, despite the fact that this indicates that more work is needed to figure out why diffusion is behaving this way in SE, this kind of acoustic mode appears to be relatively independent of that configuration. So with that, I will wrap up. The first steps are to work more with tuning SE's diffusion to remove these erroneous errors relating to topography. And I want to do further work on divergence damping in more complex model configurations, because what we saw on the first slide is that the Lamb-wave signature and these external mode signatures appear to be larger when the atmosphere is more energetic. Ideally, the sort of main takeaway message is that propagation of modes like this is physically realistic, but triggering the having natural atmospheric processes triggering these external modes is probably not very common. And so there are some tips and tricks in this presentation that can help you to diagnose, for example, if you have pretty severe numerical noise resulting from physics dynamics coupling, it may be worth looking toward the acoustic side of the spectrum to see if the large forcings are causing issues. So with that, I'd be happy to take any questions.
Great, thank you, Owen. I think there are a couple questions in the chat. So maybe I'll just read the first one from Thomas, which is, he's trying to wrap his head around a little bit of your statements on the Lamb-wave. Did you say that it's like an external gravity wave mode or a shallow water wave? If so, what is the phase relationship between pressure and temperature?
So this is, I don't have this bonus slide prepared. I was hoping to have it together, but basically Lamb waves in the horizontal are acoustic, or they propagate according to that dispersion relation. But fundamentally the restoring force in the vertical is ends up being gravity rather than anything else. If it weren't, then you would have essentially vertical propagation, a three-dimensional acoustic wave like you would expect from it, like in a non-hydrostatic model that hasn't filtered out acoustic waves. That's not a super clear thing, explanation. I'd be happy to talk more offline, but yeah.
Great. And then there's one quick clarification question from Oksana related to the last slide that you were showing results with the diffusion off. Was that in? I'm assuming the answer. She's asking if that was in CAM SE or within the home theta I. So that's, I'm guessing CAM SE. Is that right?
Yes, exactly. When these acid tests were run in even Home's hydrostatic primitive dynamical core, the errors weren't nearly as large.
And I see you were able to respond to that while you were responding to another question. So you you have good skills on that. So let's move on to the last talk of the session. We are running a little bit behind, but our next speaker is Hoi Wan, who's going to talk about the numerical coupling issues revealed by increased vertical resolution in the E3SM atmosphere model version 1. So we can see your full screen and
okay, great.
We can hear you. So
okay, great. Thank you, Kevin, and thank you, AMWG, for providing this opportunity. I'm now going to switch gears and then talk about the physics parameterizations. And I'd like to present some recent results coming from a DOE SciDAC program funded project, which involved quite a few applied mathematicians at Lawrence Livermore National Lab, plus a number of atmospheric modelers at PNNL, at a couple of universities, and at the Argonne National Lab. So first of all, a reminder of the context. The E3SM-V1 model we are working with is a descendant of CESM-1, and the atmosphere component of E3SM is a descendant of CAM5. In terms of the vertical resolution, EAM-V1 has 72 layers instead of 30. And as you can see from this figure from Shaocheng Xie's paper in 2018, within this 72-layer vertical grid, our bottom layer is now only 20 meters in thickness instead of 100 in CAM5. So the key point I would like to deliver today is that very thin near surface layers not only bring challenges related to numerical stability, but they also can reveal previously unnoticed numerical coupling issues. And we have seen concrete examples. In our cases, the coupling errors can be substantially reduced by very simple remedies, although in the future, working on tighter coupling among various processes will probably provide even more accurate solutions. Today, I would like to touch upon two examples. One of them is has to do with radiation and convection. The other is about dust life cycle. So at the first glance, these are very different problems, but hopefully I will be able to convince you at the end of the presentation that the computational problems are very similar. So first of all, first example is radiation and convection. The beginning of this little story dates back to 2 years ago at the winter AMWG meeting in 2020, where I presented some results to show that in our model, the frequency of coupling between the club and MG subcycles and the rest of the model can have substantial impact on the amount of clouds we get in the subtropical stratocumulus regions. And subsequently, when trying to understand what physical processes and the mechanisms caused this model behavior, we did a series of budget analysis for several prognostic variables of the model. And among those, we plotted the radiative heating cooling rate profiles. And here on the right, I'm showing the temperature tendencies caused by radiation in different seasons, averaged over this red box shown on the left. And one intriguing feature for us was that near the surface, we see this very strong gradient in this heating cooling rate. So going from very small heating or cooling to rather strong warming at the surface. So we did a series of analysis and simulations, and then we were able to confirm that this strong gradient was attributable to the long wave part of the radiation, not short wave. And this feature was seen also outside the Peruvian stratocumulus regions. For example, you can see it very clearly in global average, land average, and ocean average. And we further confirmed that this feature is seen only in the L72 runs, not in L30. So our understanding at this point is that this gradient is physical, because when you have a warm surface, there is going to be some temperature gradient in the lowest layers of the atmosphere. And what we are seeing here is simply that the near surface temperature profile is better resolved in a 72-layer grid than 30. The problem is mostly computational. The sequence of calculation in the model described in a simplified way is that we have radiation sequentially split and immediate and followed by deep convection and then followed by turbulence. And such a sequence, you can imagine that if we have a strong near surface heating that is not diffused by turbulence, we can accumulate CAPE. And in case the time step is also long, this accumulated CAPE can cause spuriously strong or frequent convection. In order to verify this hypothesis, we did some sensitivity experiments. So we kept all the parameterization costs in the TFIS, BC, and AC subroutines as where they were. The only thing we changed was that we held off using the relative heating or cooling rate in updating the temperature, and then we kept that tendencies until deep convection has been calculated. We are about to compute turbulence, and then at that point we use the relative heating and cooling rates to update the temperature profile in the atmosphere. And this is effectively doing a parallel splitting between radiation and deep convection. We expected that we would see some impacts in regions where radiation has a relatively large role in the CAPE budget. And that was indeed what we saw. So here, I'm showing you the 1 year mean low cloud fraction simulated by the original CESM-2022 in the left panel, and in the rightmost panel is the relative difference caused by this parallel splitting between radiation and convection. And you can see in the subtropical trade cumulus region specifically, we are seeing changes on the order of 5% to 50% in low cloud fraction. The nice thing about this change is that previously we already knew that CESM-2022 had a relatively strong time step sensitivity in its present day climate simulations. And here on this slide in the left panel, we see how much reduction in low cloud fraction we would get if we simply took CESM-2022 and reduced the physics time step from 30 minutes to 5 minutes. And with the parallel splitting between radiation and convection, combined with the so-called dribbling that I presented 2 years ago, we are able to largely remove this sensitivity. And we also check that when we use a short time step, the original model and then the revised splitting would give very similar results, which confirms that by changing the splitting, we are not changing the physics, we are only reducing the numerical errors. So that was nice. And now I will switch gears and talk about dust life cycle. CESM-2022 has a known problem of dust life cycle being very short. So here I've taken some numbers from a manuscript by Yan Feng from Argonne. He showed that in CAM5, the global mean dust life cycle is about 2.5 days, but in CESM-2022, we have only 1.9 days. She also showed that by reverting the vertical resolution to 30 layers, you can pretty much restore the original dust lifetime. So to understand why there is this sensitivity, it's useful to take a look at the process rates in the dust life cycle. Here on the left part of the slide, I'm showing you the 1 year mean dust burden and emission fluxes. And on the right, the details really don't matter, but then it's on the right, I have the different process rates averaged over the emission regions. The shapes of those profiles pretty much match our imagination, But the interesting thing you might or might not have noticed is that the numbers in the lowest model layer are usually off the chart on this slide. In order to bring the numbers back to the chart, I had to enlarge the range of the x-axis by a factor of 100. Now with this rescaled plot, you can see that pretty much in the source regions, the dominant processes are emission and dry removal and turbulent mixing. And pretty much everything else and in other layers are negligible, at least in terms of the regional averages. So now the problem is this. So we have in our model emission calculated and then dry removal and then turbulence. So in the real world, dust often is emitted in relatively turbulent environment, and those eddies are very efficient in lifting the particles up. In the model, however, the particles are emitted only to the lowest layer and temporarily trapped there. And then we calculate removal, which end up being very high biased. And then the turbulence only get a chance to mix the particles after the removal is calculated. So this is another example of strong source and the sink terms treated with sequential splitting and very long time steps. And so having understood this, then we did some very simple changes in the code, similar to what we have done for the radiation example. And basically, we now use a parallel splitting between emission and dry removal. And as a result of that, we were able to restore the dust lifetime to a value that is within the expected range. And also now with the revised sequence, if we do a L30 simulation and compare that to L72, the results are very similar. We no longer see the very strong sensitivity to vertical resolution. And in terms of dust loading, we see a significant increase of dust burden and also the global distribution of the mixing ratio. Pretty much everywhere over the globe, we see increases in burden or mixing ratio over 20%. And at some places, the increases are even stronger. So that brings me already to my last slide. Having understood these two problems, we realize that essentially we are seeing the same old coupling problem, which is sequential splitting being applied to strong sources and sinks together with very long time steps and causing very large coupling errors. In these two cases, however, it's the higher vertical resolution that has has introduced new pairs of strong sources and sinks that we either were not so obvious there or not noticed previously. And in these two cases, we were able to switch to parallel splitting and substantially improve the results. But certainly this simple parallel splitting is not the best we can do. If we further implement some more advanced coupling schemes, for example, by combining numerical solvers of different processes, the results can probably be further improved. And with that point, I want to echo what Joao Teixeira said on Monday, that less isolation between processes is going to help us in improving the model results. And last point I want to mention is that for us, it has turned out that budget analysis is a very useful tool for identifying, understanding, and addressing coupling issues. We are now trying to do a very systematic budget analysis for all prognostic variables in our model, hoping that this analysis will give us more clues for how to further improve the numerical coupling for future versions of the model. So with that, I can take questions.
Great, thank you. We have a few questions in the chat, and maybe I'll just start with a couple that I'll read off that I think are relevant. So related to one of your earlier slides, you talked a little bit about the process ordering within EAM, and
you want me to just?
Yeah, go ahead, Adam.
Yeah, the process ordering in your slides showed radiation, deep convection, then turbulence.
Right.
And radiation in CAM is after turbulence. So I was a little confused on whether maybe E3SM moved radiation or not.
No, we didn't. But so time integration, when you use sequential splitting, is a loop, right? So what I mean here is that you calculate radiation in one time step, and then you go through the T-phase AC, which doesn't do much to the temperature. And then we have dynamical cool, and then you get deep convection, right?
So in between radiation and deep convection should be T-phase AC and dicore, right?
Yes. Although in this problem, T-phase AC and the dicore don't seem to do much.
Okay. Well, interesting. And then the second point I want to leave it to other people, but that's really important. And I think we need to look into that in CAM because it actually seems to be a problem of where we actually put club when we implemented club, and we didn't do it too soon. This dust ordering issue wouldn't have been a problem in CAM 5. And so it's all about the choice and where. Okay, go ahead.
There is one caveat though. So club, well, I suppose E3SM is the same as CAM in that aspect. So club does mix heat and water vapor and gases and ice cloud ice, I think. But aerosols are not mixed by club, right? So aerosols are mixed by the so-called job mix nuke subroutine. So it's and then that job mix nuke subroutine, if I understood correctly, in CAM 5 was also located in T-phase BC, right? So if that is the case, then I think CAM 5 already had this problem, but because we had 30 layers, not 72, not extremely thin layers, the problem was not as obvious.
Okay, that's a good point. So it's the end drop.
Yeah, drop mix nuke. Yeah. Okay, activation and mixing. Yeah, activation and mixing.
Okay, I'll have to look closely into that. Thanks.
You guys are using a lot of good subroutine and variable names that you would only know if you're in the code. So
right.
One quick clarification question I think that came from Andrew was related to, so even though EAM kind of branched off of CAM and CAM 5, that EAM v0 is actually very similar, is more similar to CAM 6, right? In the fact that it has club, MG2, the new ice nucleation scheme. So that, I think that was just a clarification for earlier in your talk.
V0, I think I don't know whether there are other E3SM developers here who can correct me, but I think if we run E3SM with V0, we don't have club. We still have the user
so
thing.
Yeah, so V0 is CAM 5. Very similar to CAM 5,
it's very similar to
V1 is more similar to CAM 6, right?
Yeah, I think so.
Yeah, okay.
Yeah, I think so.
Okay, cool. One other quick question, I think that was from Julio, was could you reproduce this cloud time step sensitivity, or do you think you would be able to reproduce that sensitivity in a single column setup? I don't know, Julio, if you're on
this sensitivity.
Yeah, that's the one.
I would guess so, because this is mostly about physics coupling, right? So less of a physics dynamics coupling problem. So we might be able to reproduce this in a single column setting, but I haven't looked into that yet.
Okay, thanks.
Yeah.
Okay. Well, so we kind of ran over a little bit, and that's because we had some good good questions after I think each of our talks in this session. So what I would like to encourage everyone is that when we're going to come back, so we'll take a break now, we'll come back in an hour to break into the high resolution and hierarchical modeling session. And then in addition to a specific discussion after that, there is a full kind of 40-ish minutes left for a all hands discussion. And to really think about some of the discussion we had this morning about the model intercomparisons, but also the die-core and coupling to bring ideas and discussion and thoughts as we work towards Camp 7 to that discussion later this afternoon. So with that, I just want to thank everybody for all the good questions and give another round of applause, virtual applause to our speakers this morning. And we will see everybody back here in about an hour.
Thanks, Kevin.
Yep.
So Kevin, Julio, if you're still here, I am teaching at 3:30 my time later today, so I will miss the final discussion. I'm just as a heads up, unfortunately.
Yeah, I have to as well. So
you have to as well. So
I think Julio had to sign off because he had a meeting he had to get to here too. But I'll let, maybe we should send him in, or I'll be on the first part. I'll send him a message then.
Oh yeah, or Elizabeth is here. Yeah.
Okay.
Okay.
Well, I know he's planning to go to breakout rooms too, so those won't be recorded, but it does seem, well, you know, I could just send him a chat to see if he's going to have everybody come back and have the rapporteurs give a summary, which will then be recorded. So when they come back to the main room,
okay,
you'll be able, I could just make a note to see where in the YouTube stream you can pick that up, or the YouTube does take a few hours to process anyway.
Okay.
So you'd be able to see it by later tonight or by tomorrow.
Okay. Yeah.
Okay, sounds good.
Yeah,
it is
so
really hard.
I stay on, you know, until I don't know 3:25 my time, but
yeah,
need to
yeah,
run,
okay.
unfortunately. Yeah. Okay, thank you.
Great, see you later. Thank you.
Yep.
Hi, Julio. I was just writing you a message.
Oh, hi. Yeah.
So when we go to the breakout rooms and there's
Mhm.
small group discussions, are you going to have the rapporteurs, everyone come back to the main room and give a debrief?
I think, yeah, a short 1-2 minute debrief from each one. Yes.
Okay, perfect. Because then that will be part of the recording that people can go
Mhm.
back and
Okay.
see, because breakout rooms are not recorded or streamed.
Understood. And I just got an email from Nick Davis. He's going to do it. So we've got, I guess we have 8 now.
Perfect.
All right. Oh, people are starting to come on.
Julio,
Yes.
can you hear me? Yeah. Are you still planning to send a slide for the breakout room?
I will. I'll do
Okay.
it. I'll do it later.
Okay. Okay. Perfect.
All right. Hi, Dave. All right.
Meeting going smoothly?
So far, yeah. I think this session should be pretty interesting. A lot of nice high resolutions, always interesting.
Yeah. Aspirational.
Yeah. Hey, Andrew.
Gotta unmute myself there. I moved my office around now. I'm totally backlit.
Where are you now? Are you down the hill?
I'm down at Foothills.
Okay.
But I got a new stand-up desk, so I had to swap some stuff around. So now I have to get better lighting to call the production people.
Yeah. At least you're not emerging kind of randomly out from behind your background. That's
what? Oh, yeah. Maybe if I turn, I don't think that helps at all. Then you can just see all the junk on my whiteboard.
all right. We're rapidly adding participants. I'm just going to go ahead and introduce you so we can get started at 12:20. Okay.
Okay.
All right. Welcome back, everyone. This is the last session of the AMWG whole atmosphere CAM-CHEM working group meeting. We're having a session on high resolution and hierarchical modeling. The first talk will be from Andrew Gettleman, talking about progress in the system for integrated modeling of the atmosphere. Next generation community atmosphere model. I'm not going to read your title, Andrew. Why don't you just go ahead and get going?
Okay. Can you see the slides?
Yeah.
Okay. So I'm going to give an overview of SEMA, the System for Integrated Modeling the Atmosphere. There are 4 SEMA science leads: Mary Barth, myself, Hanli Liu, and Bill Skamrock, representing sort of different areas of the science, and a software engineering program manager, Jordan Powers. I gotta click there. There we go. So the SEMA vision is basically to unify in-car-based community atmospheric modeling. Each one of those words is fairly carefully chosen for what it means. Today, you can see on the left, we basically have a whole bunch of different models and configurations. Particularly, we have sort of CESM, which is WACMX, CAM, CAM. And then we have MPAS and WRF, and those things extend all the way down to then having LAS and process models. The goal with SEMA is to actually integrate all that into a common infrastructure. And that's the overall goal. It's not a single model, it's a configurable system. It's atmospheric models within an Earth system model, within a coupled system. That Earth system model we've chosen for the moment is CESM. It's a minimal set of interoperable components. It doesn't mean everybody's using the same thing for all these configurations. There are different physical, chemical, upper atmospheric parameterizations and dynamical cores involved. What it is common infrastructure methods for sharing and extending diagnostics, educations, tutorials. The goal is keep up our back-end infrastructure with reduced duplication of effort and enable sort of more things and more parts of the hierarchy of atmospheric modeling. It's a community working together also towards frontier applications. So it's not just software, it's also people and it's science. And this has been developed with a series of different things. We have a website, sema.ucar.edu. It has a bunch of history of what's going on with this. So the best way to visualize SEMA is if this is CESM and I've blown up the atmosphere model and called it SEMA, there's a series of physics and chemistry packages, parameterizations, there's a physics dynamics coupling layer, there's dynamical cores, and then there's data simulation. Don't worry about where the data simulation sits. That's a whole discussion in and of itself. 3 dynamical cores are listed here. MPAS, model for prediction across scales, as a dynamical core, the spectral element dynamical core, and FE3, which we've talked about earlier today. So let's just blow it up and look at SEMA. And what SEMA is the opportunity to configure this system in different ways. And most of these ways sort of already exist in some form. So SEMA climate, so CAM7 is basically the CAM physics, the minimal musica aerosol package, and the spectral element dynamical core. That's kind of where we're going. And the key here is that SEMA is the next generation infrastructure for CAM. So you can think of CAM as being SEMA for climate. They're sort of equivalent. It's not clear we're going to change. Obviously, CAM branding is going to stick around, but that's basically SEMA climate is CAM7. We also have a polar version of this, which uses a regionally refined version over the polar cap, for example, and that happens to use the spectral element model with regional refinement. There's also a musica version with chemistry that has full atmospheric chemistry. So I've highlighted that. And it also has regional refinement. This is over the continental United States. Those simulations have actually been released. I'll show a slide on that. There's a geospace version that adds in the plasmasphere and thermosphere. It adds in coupling and geomagnetic grids. Sometimes it's run in data simulation mode. And that uses also a high resolution version of the spectral element core. And then there's SEMA weather, which is a blending of the WRF physics and the CAM physics. It'll show some examples of where we're going with that. Also uses data simulation. This is using a non-hydrostatic core, so the MPAS dynamical core. So what's new about this? Well, we're really pushing the envelope of CESM, coordinating across atmospheric working groups, chemistry, AMWG, WACM. We're enabling new science with new workflows, particularly for high resolution. That's regional climate, climate extremes, weather phenomena. Also prediction eventually is on the list. SEMA is providing additional resources or infrastructure across CESM. We're adding this the non-hydrostatic dynamical core integrated into CESM. That's one of the things we've done recently. We've also been working on scaling for high core counts, portable physics, GPU accelerators, object-oriented programming. So lots of things that are a benefit across the institution, across the traditional applications for CAM. And we're allowing sort of diverse workflows for CESM and things we were talking about earlier with the necessity to have more different workflows, and Christian was talking about different grid tools. We're also trying to push those out. So one of the keys is that SEMA is not defining CAM7 or CESM3. The CESM working groups define what's in the CESM atmospheric models, and SEMA is sort of the infrastructure and the framework and the science group that's helping produce those models. It's a lot of the same people, as you can tell. It's a small project. We're making advances through leveraging other work and complementary science goals. There's a lot of information on the website. It was an internally funded project over the last couple of years. Last year, sort of SEMA V1, we created a bunch of applications. We had a big meeting on that in November that many of you attended. We're now moving towards moving towards a convective permitting system has been really challenging with CESM. And the other challenging thing is building a culture of development across the different communities, both on the science and the infrastructure side, throughout NCAR and throughout the community. So right now we're developing applications, we're doing infrastructure updates, we've got a soft ramp up and small seed funding, which I can talk more about resources and things like that later. So the current applications look something like this. We've got a polar prediction model, 25 kilometers refined CAM spectral element Arctic. It's coupled with Greenland. That can be actually run fully coupled. We have a comp set for that. We're pushing down to weather resolutions, 7.5 kilometers global non-hydrostatic, and looking at 60 to 3 kilometer refined mesh over the United States. I'll show some examples of this, and Dave Randall will talk more a little bit about that as well. Climate extremes, we're looking at refined mesh over the United States with SE and MPAS. South America grids, that Patrick Callahan's been working on with the SE data set, and also the grid tools and other comp sets in development. There are these regional air pollution runs with the music of V0 that I'll mention, and there's coupled space weather simulation. So WACM-X with SE and the CSLAM version of that, the parallel transport driven by Gamera, the magnetosphere MHD model at 25 kilometers. And there's also simulations available for that. So you want more information, cema.ucar.edu. There's configurations and simulations prominently. We've got a refined mesh component set for the Arctic, fully coupled, regional climate, grid tools, music of V0 regional chemistry, modeling output, and WACM-X simulation output as well. And there's other configurations in development that I'm showing examples of too. So Adam has been doing a lot of work with others on the polar grid. So there's really nice animation that the VisLab put together. Search YouTube for this Greenland VisLab, and you can see this high resolution, this Arctic GRIS, 1/8 of a degree, so down to really fine resolutions of 12 to 14 kilometers over the Greenland ice sheet, running with a Greenland ice sheet model. And there's an Antarctic grid, which is coming hopefully this summer as well, in addition to these Arctic grids. And there's some really nice pictures of this on that YouTube video showing what happens at 1/8 of a degree. You really can start to do the surface mass balance more correctly because you're getting the edges of the ice sheet, and we get streamlines for katabatic winds coming off the ice sheet as well. So Dave Randall's going to talk about earthworks, which is pushing towards sort of extreme convective permitting resolutions globally. So we're up to 7.5 kilometers. This is an aquaplanet run using essentially CAM6 physics, non-hydrostatic dynamical core, pushing all the way to 3.75 kilometers, which is soon. So Dave will talk more about this and about the earthworks project, which is integrated sort of with the SEMA goals, and SEMA's working back and forth with earthworks to support that. Just a quick slide. This is some stuff that I think some of you have seen. These are runs in red with CAM-MPAS at low resolution. So these are just climate runs at 120 kilometers compared to CAM6 finite volume, so in blue. And basically it produces a reasonable climate. There's some differences here, but it's pretty much, for all the metrics we've looked at, it looks pretty good. So for example, and in the dynamics, here's just a zonal wind. The top two panels are FV. On the left is the zonal mean zonal wind. And then on the right is the difference versus era interim. Same for MPAS on the bottom. Really not clear any one of these is better than the other. So we're actually doing pretty well, we think, on climate simulations, and we have basically full energy conservation now. We've also pushed this to climate extremes. So we have a variable resolution version of CAM-MPAS. This is 60 kilometers globally, so about half a degree, but it goes down to 3 kilometers over this region here. So you can see the 60 kilometer CESM-MPAS resolution is in the middle. That's the topography. WRF 4 kilometers on the right, CESM-MPAS 3 kilometers on the left. Basically the same. We're basically running at mesoscale resolution with CAM6 physics, and this is work that Xingying Wang has been doing under the Earthworks project at NCAR. And what's really cool is this is producing some really nice precipitation output. So this is wet season, November to March precipitation over the Western United States for 5 years. And you can see PRISM is observations in the center, WRF is on the right, CSM is on the left. CSM is actually doing better than WRF relative to the observations with straight up CAM6 physics. And you can look at the frequency plots again, you can see the same thing. WRF is actually overcooking some of the extreme precipitation, and CESM is doing a really good job of getting the high frequency precipitation all the way to pretty extreme amounts of 60 millimeters per day or so. So actually, we're really excited about using this for climate extremes and using it also as a regional climate model. It's not super expensive to run. You don't need a Department of Energy machine to do it. It runs pretty well on our current machines here. Chemistry, so the community music version 0 simulation is CESM 2.2. It's spectral element, regional refinement, again, 14 kilometers over the United States. You can see what that resolution gets you. It gets you New York City, Knox, and it separates it actually from Philadelphia and Trenton, New Jersey, interestingly enough. And you can see all the cities in the Northeast, and you can look at the surface ozone. So there's actually 2 years right now. I think they're running more, and there's details again on the Musica Wiki or on the SEMA webpage. So this is from Han-Li Liu. These are some of the geospace simulations. It goes WACM-X going all the way up to 500 kilometers. On the left is the thermosphere zonal wind perturbations. These are gravity waves, and that tilt with height matches the observations quite well, which is one of the first times that's been done. And on the right, this is total electron count perturbations from these simulations. This is the first time this has really ever been simulated. And it's really sort of high resolution reacting to, again, sort of gravity waves in forced from the lower atmosphere. And you can see these sort of migrating tides that are happening through the course of the day in these simulations. So our one or two more slides, our near-term plans, continued development of SEMA applications, supporting CAM7 development for physics and configurations. That's one of our primary goals right now. And we're also pushing towards convective permitting resolution in CESM. So non-hydrostatic, regionally refined, and globally uniform meshes. Two of these targets, regional climate is 60:3, weather is 15:3, starting with CONUS. And we also have these global uniform target at down to basically 3 kilometers or 3.75 kilometers. We're continuing development of these polar configurations, moving into the Antarctic. And there's parallel advancing of the chemistry and aerosols, especially with these regional meshes. And the geospace is moving to a two-way coupling with magnetic grid. Right now, it's just one way. So if you're interested, talk with us. And just to note, we got slow development of new infrastructure and workflows that's coming along, and we're working to prioritize that and get the resources to finish that. I think I will stop there.
Okay, I thanks, Andrew. I think we have time for a few questions.
Talk to me, Simona. It's Xing Huang is doing a lot of that work over the US.
So I had a quick question about the comparison you showed over, it looked like California, the Sierras, between WRF and MPAS.
Yep, let me go get it.
WRF had more, looked like WRF had more extreme, well, it had higher precipitation values. I'm wondering, were you using a convective, did your run have a convective scheme on?
I think we did leave the convective scheme on.
Okay.
It's not a huge impact on these simulations because it's orographic precipitation mostly over the wet season. So
got it. Okay.
Convection is not, we picked the easy target where we didn't have to worry about convection. We're now trying to set this up over the central United States in summer. And the first thing we're starting to have to worry about is what do we do about convection?
All right. Oyvind Seeland is asking, what is the vertical resolution in the California? And I guess we're talking about the same.
Yeah, 58. We're 58 levels. So we're actually doing the same higher vertical resolution with the low top model that's been talked about earlier in the week. So we moved, when we're doing all these, our target is to use that same, for all these simulations, actually across SEMA, we're basically moving to the same vertical resolution, even regardless of dynamical core, for simplicity's sake.
Okay. And you see the question from Peter?
No, we're not moving anywhere, Peter. It's just a statement. It's for the high level programmatically. It's an atmosphere model inside of an Earth system model. That Earth system model is CESM. We're not going anywhere. Sorry if that wasn't clear.
If people have more comments, either put them in the chat or save them for the discussion. I think we should move on now to the next talk on earthworks from Bill Randall. So you want to take it away? Sorry.
Yeah, Bill is my cousin.
Dave Randall. Sorry. Sorry.
He isn't really my cousin, but we kid about that.
It's a long day. Sorry.
Yeah, no problem. I have a brother named Bill. Yeah, I'm here to talk about earthworks and long list of authors here. The project is led out of CSU, but some of the funding is also going to NCAR. We've been funded since August of 2020, so we're about a year and a half in. Earthworks is based on CESM, but it's not a CESM project. It's a university-based project. And as Andrew mentioned, we have certainly goals and some model components in common with CEMA, but Earthworks is distinct from CEMA. So the goal of Earthworks, as the first paragraph says here, is to develop a global coupled model based on the CESM in ways that I'll explain here, that uses a single uniform 3.75 kilometer global grid for the atmosphere, ocean, and land surface. So one grid to rule them all. And for this audience, I don't need to explain the benefits of cloud permitting resolution for the atmosphere and eddy resolving resolution for the ocean. And we firmly believe that if you're going to do very high resolution in both the ocean and the atmosphere, then a single grid for both is the right way to go. It enables a lower operation count, less message passing, and reduced memory requirements relative to models that use different grids for atmosphere and ocean. So the components of Earthworks are the MPAS atmosphere, which Andrew has already talked about, including a resolved stratosphere. The results I'll show you today don't have a stratosphere, but that's where we're going. High resolution CAM-like physics. We'll see how it evolves. It's a non-hydrostatic model, and I'll show you results later that have the convection, deep convection stream turned on, but you'll see that it kind of dies away at high resolution. And we're using the community physics framework. The ocean model is the MPAS ocean model, which can use the same grid as the atmosphere. That model is developed at Los Alamos, and Phil Jones of Los Alamos is one of the authors of this paper. So this ocean model is being used by E3SM, the DOE or system model. And also they have an MPAS sea ice model, so we're using that too. And of course, the land surface model is needed, and that will be CLM, same as in NCAR, standard CESM. And we're using, importantly, the community mediator for Earth prediction systems, or CMEPS. The CMEPS mediator shown over here on the right side of the slide that essentially coordinates the activities of all these various components that I already mentioned. So all components of the model are now working inside the CESM framework. It's quite a bit of work to get that done. And as Andrew showed you in the previous talk, we have a 5-year simulation with realistic geography and a data ocean using a 100-kilometer version of the MPAS atmosphere. This is running inside CESM, and the results from that look fine. Well, I'm going to show you some results from MPAS Aquaplanet. And as the title here says, we have a bootstrapping strategy. We start at low resolution, 120 kilometers, or essentially 1 degree, and work our way down to the 3.75 kilometer target resolution. So we actually have results today down to 7.5 kilometers. I'll say more about 3.75 here in a second. And there it is. We are able to take time steps with the 3.75 kilometer grid currently, but there are memory issues, and in particular, we can't write restart files. So it's not really working yet, but we're getting close, and the memory issues are being worked. So here's a comparison of total column water vapor, 120 kilometers on the top left and 7.5 kilometers on the bottom right. You can see the structures look basically similar, but there's certainly more detail here in the higher resolution version. Here are some precipitation results. And so on the left, you see, by the way, APE just means aquaplanet. The red curve, sorry, the blue curve, sorry, the black curve, first of all, is 120 kilometers. Blue is 60, red is 30, green is 15, and the sort of pink color is 7.5. And we have here a simulation that starts coarse and gets progressively finer by bootstrapping and runs for a total of 380 days. No seasons, of course, on the aquaplanet. What you can see over here is that the convective portion of the precipitation is most of the total or a large fraction of the total at 120 kilometer grid spacing, but decreases by about a factor of 4 at 7.5 kilometers. So yes, we are running in this case with a deep convection parameterization, but it kind of goes to sleep. Our plan for the global 3.75 kilometer model is not to use a deep convection parameterization at all. Here are a couple of movies showing precipitation on the 120 kilometer mesh on the left side and the 15 kilometer mesh on the right side. I don't have a movie on the 7.5 kilometer mesh, but you can see, okay, the domains here go from what, 15 south to 15 north. So you're just looking at the tropics. There's a very clear double ITCZ structure here. Not so clear here. And the overall structure of the precipitation looks very different, even though the zonal means actually look quite comparable. We have successfully run the coupled model. So that means atmosphere, ocean, and sea ice and land surface. And the work to get this done was done by Don Dasley, whose picture I put here. Don is at CSU. And so he had to essentially port the ocean and sea ice models into the CESM infrastructure, and it took a while. And we had a lot of help from Mariana and her team, and also from Phil Jones at Los Alamos, and other people listed on a later slide. So I'm going to show you results at very low resolution, well, 1 degree, from this coupled model done on Cheyenne using CPUs. I'll say more about GPUs here in a minute. So here are just a few panels showing results from the coupled model. This is a little bit more than a 1-year simulation. This is showing precipitation in December. The run actually started in January. So this is the 12th month. And you can see it looks like planet Earth. Here's sea ice. The sea ice was started with uniform 2.5 meter thick ice forward of 70 degrees north and 60 degrees south. And what you're seeing here is the sea ice area fraction for September of that first year. So you can see that it's, a lot of the ice has disappeared in the Northern Hemisphere, as you would expect. And there's also been some change in the Southern Hemisphere. This last panel shows the change in sea surface temperature after one simulated year. So comparing the 2nd January with the 1st January. And the largest numbers you see here are on the order of plus or minus 3. Most of the larger differences are in the Southern Hemisphere. And we don't have a detailed analysis of why this has happened. But at any rate, you can see that the ocean is basically still looking like an ocean. CAM-MPAS performance data. I don't know whether Peter may have shown this slide earlier this morning because I couldn't listen to your talk, Peter, but this shows tests of performance with different numbers of tracers. The model is actually running the dynamical core plus a certain number of tracers and a kind of Kessler microphysics. The vertical axis here is time to simulation. So smaller numbers are better. That's what this means. You're seeing the spectral element model with and without CSLAM, the latitude, longitude, finite volume model, the old finite volume model, the new one, FV3, and then MPAS. And you can see MPAS is looking pretty good here. They're all, it's actually pretty similar to FV3 with a smaller number of tracers, but it improves relative to FV3 with higher numbers. It's not as fast as the older finite volume model, but that model, I believe, is on the way out. So conclusions and next steps, and I have one or two more slides after this. In aquaplanet tests, the MPAS atmosphere has been run with the 7.5 kilometer grid spacing, and we're working to do 3.75, which is our target grid spacing. We have successfully ported MPAS ocean and sea ice into the CESM framework, quite a bit of work there. The MPAS atmosphere dynamical core and the ocean dynamical core can now be run on GPUs. So this is the first time I've mentioned this, but it's obviously important going forward. Derecho, the next machine, will have a lot of GPUs. And of course, there are lots of other machines out there in the world with plenty of GPUs. So we are currently in the process of porting the atmospheric physics to GPUs. And Earthworks, in the process of doing these various steps I've listed, is helping to identify some limitations of the current CESM infrastructure. This is a positive way of putting it. So we've run into a few problems, and the problems have been worked, and we're very grateful to Mariana and others for helping us with that. We're optimistic, based on the results so far, that by 2025, which is the year when Earthworks ends, the coupled model will produce at least one simulated year per day with a 3.75 kilometer grid on a sufficiently powerful machine. So last slide, as I said, Earthworks is not a CESM project, but we are working to maintain the compatibility with the evolving CESM code base. So we're not going to get out of sync. And we will persistently engage with CESM through talks like the one I'm giving right now, and also with community scientists. And in 2025, Earthworks will pitch the possibility to CESM leadership of that time that Earthworks could be a supported configuration of CESM going forward. Obviously, Earthworks doesn't control that, but we hope that CESM management will adopt it with enthusiasm when the time comes. So final slide, acknowledgements. ESMF and CESM Software Engineering Group teams for their help, and also the list of people shown here. We appreciate all your efforts. And I didn't list Phil Jones here because he's an author of the paper, but we certainly appreciate his help. So let me get out of there. Time for questions.
Looks like Thomas Toniazzo has put a question in the chat.
Yeah, actually, I'm having a Zoom problem. I can hear you. Can you hear me?
Yeah, I can hear you.
I can hear you, but I can't see the chat or anything like that. So
well,
I'm not going to touch anything on my screen because I don't want to terminate my session. So go ahead and just ask the questions.
I was just curious. You dwelled on the technology challenge of getting this thing to work at all, and I wonder, are there any science objectives in Earthworks as a project?
Yes, we have science objectives. That slide was cut in an effort to keep the talk down, but I have it here. Let me just find it for you. Here we go. See, I'm not sharing anymore, or I am. No, I still am.
We see the science questions.
Okay, good.
Well, they just disappeared when you went to full screen.
Yeah, I probably went backward. Sorry, let me find it for you here. The problem is it's a skipped slide.
Mm-hmm.
So when I go into play mode, you don't see it. I will unskip it and play. So these are very broad, of course, but tropical cyclones, frequency and intensity with the target resolution we should be able to get very realistic intensities. And how will this change in a future warmer climate? This is a question that can be addressed in time slices. How does the mesoscale organization of cloud systems affect the global circulation and climate? A lot of us are interested in convective self-organizations. This will be one aspect of that problem. With 3.75 kilometer resolution, we don't think we will need a parameterization of any of the various types of gravity wave drag. And we should be able to study by explicit simulation the interaction of these relatively small scale gravity waves with the larger scale circulation. And then, as Andrew mentioned, these high resolutions, you can see cities. And so we'll be able to look at how climate change manifests on the scales where people live, basically. So it's very broad brush, but here's a list of science questions.
Okay, there's also a question from Rich Neal. I think we'll take that and then we'll move on.
Okay.
You want to go ahead, Rich?
Yeah, I'm sure you've grappled with this before, but the role of the ocean, how do you see that MPAS coming in as part of the CSM based on the, with respect to the fact that, MOM is just getting off the ground for the new ocean?
Well, that's going to be a management decision. As you know, CESM is currently supporting multiple dynamical cores for the atmosphere, and this has been true for a long time. And my understanding is the plan is for that to continue into the future. I don't see why the same thing can't be true for the ocean, but of course, that decision will be made by other people.
Okay, I'll have to let Gokhan weigh in. Can you do it quickly?
Yeah, I mean, we had many discussions already, Dave. As you know, ocean is not like the atmosphere. You cannot simply switch the dynamical cores, and that's the problem. Physics is strongly engaged with the dynamical core. And this is not also coming from the CESM SSC membership or working groups directly. So those are the impediments that I can see right away. But you and I discussed those issues before in any case, so you're aware of those.
I suggest that we postpone further discussion to the discussion section if everyone will still be here. In any case, I do think we should move on because we're 3 minutes late.
Yeah, I have to go back into the UCAR board meeting, so I will not be here.
Oh, okay. All right. Well, thank you, Dave. And now we're going to go on to the talk on tropical cyclones by Alyssa Stansfield. Do you want to go ahead, share your screen and get going?
Yes. Okay, can you see my slides? Maybe they're coming up.
Something's loading.
Okay.
Yeah.
Okay, great. Thank you. So hi, everyone. My name's Alyssa Stansfield, and I'm going to be talking a little bit more about some applications of CAM and specifically kind of a simpler setup for CAM. And so this presentation I've worked on alongside my advisor at Stony Brook, Kevin Reed, as part of my PhD thesis. And so I'm going to be talking about tropical cyclone precipitation. Okay, so flooding from tropical cyclones is one of the deadliest and costliest hazards. And so basically, we want to try to understand how flooding from tropical cyclones will change in the future. I mean, flooding is obviously impacted by quite a few different factors, but for my work, I focused on precipitation. And so, many studies have tried to look at how TC precipitation will change in the future. This figure on the left is a figure from kind of a summary paper, Knudsen et al. 2020. And if you look at the global median change of TC precipitation, kind of summarized from many different studies, which is the one shown in the red circle, they predict about a 14% increase in near storm precipitation for 2 degrees of warming. And so this is in line with the kind of theoretical Clausius-Clapeyron increase in atmospheric moisture with temperature increase. However, the exact results really depend on the model and the precipitation metric you're looking at and kind of other details of the analysis, as you can see from kind of the broad box and whisker plot. And so these large differences between the different studies are likely due to differences in the future dynamic forcing. in the models. And so to try to look further into this problem, we simplified CAM. So we use the RCEMIP comp set with CAM version 5, which Levi Silvers talked a little bit about this in his presentation this morning. So I use very similar simulations to Levi, except I add rotation so that tropical cyclones are allowed to form. And so I ran 11 different simulations with this globally uniform SST varying from 295 to 305 Kelvin in 1 Kelvin increments. So this covers kind of the SSTs that we see in the real world in the tropics. Simulations are run for 2 years. The horizontal grid spacing is about 28 kilometers or so over the entire globe using the SE dynamical core. And so quickly, what do these simulations look like? Here's an animation of wind speed. And so all those little kind of dots you see moving around are tropical cyclones. So they form kind of in the tropics and subtropics, move poleward, and eventually they kind of accumulate near the poles where they either merge with each other or die off. And this plot on the right here is from Shavas and Reed 2019, where they used very similar CAM simulations that are shown as the control in the orange. And they're comparing the zonal mean annual genesis density of tropical cyclones in this control simulation versus an AMIP simulation. And so we see that although there are differences more in like the mid latitudes, the genesis density is very similar in the areas where tropical cyclones are really forming in the real world. So while these simulations, obviously look very different than the real world, I think they can be used in some context to, study tropical cyclones in the real world. And so for my simulations with the varying SSTs, I'm looking at a couple different TC characteristics to start. So as the sea surface temperatures warm, which is shown on the x-axis, the SSTs of the simulations, we see that the global number of tropical cyclones decrease. The outer size of these tropical cyclones increase on average. And then when we look at what percentage of the globe is covered by these TCs, we see that slightly decreases. So the decrease in number is kind of outweighing the increase in size slightly. It's not shown here, but the global mean precipitation from TCs slightly increases with SST as well. Looking at lifetime maximum intensities of these storms, as expected, as the SST increases, the average TC is more intense. And what we see from these distributions of lifetime maximum intensity, we see that most of them are bimodal in nature. And so that's interesting because that's something that's actually seen in observations as described in Lee et al. 2016. And they relate this bimodal nature to instances of rapid intensification of tropical cyclones. And we also see in our simulations that the instances of rapid intensification do increase in the warmer SST simulations, which is interesting. Moving on to TC precipitation. So the figure on the left here shows the relative frequency of different precipitation rates within TCs. And so if you look at the x-axis, those are different precipitation rates, and this plot shows you the frequency within TCs, I guess, that this precipitation rate occurs. And so we see that, especially at the extreme end, it's a little hard to see, but there are more frequent, very extreme precipitation rates within TCs in the warmer simulations compared to the cooler simulations. And then if we move over to the plot on the right, this shows the precipitation amount that comes from each of these precipitation rates within TCs. And so we see that generally most of the precipitation for all the simulations comes from these very high precipitation rates. And as the SSTs warm, more of the precipitation comes from the very extreme precipitation rates as well. Here's just some composites of TC precipitation, going from the 295, so the coolest simulation, all the way on the bottom right to the 305 and the warmest simulation. And I'll also note that the precipitation analysis here and in the last slide or two has been limited to 40 degrees south to 40 degrees north, because we kind of wanted to avoid the like accumulation of TCs at the poles, because obviously that's not a very physically relevant, something that happens in the real world. So we limit the latitudes to kind of avoid that complication. And so from these composites, we see that the TC inner core precipitation increases with SST, as well as the size of the precipitation field also seems to increase as the SST increases. And so this joint distribution plot kind of shows the change in the 99th percentile of TC precip with SST is on the y-axis and storm intensity, which is on the x-axis. And so basically each of these little boxes shows the median of a distribution of like thousands of TC snapshots at a specific SST and at a specific intensity. And so the main takeaway from, I don't want to go into this too much, but basic result is that TC 99th percentile precipitation increases with increasing SST and with increasing TC intensity. So this is what we would kind of expect from theory. And so next we tried to break down this precipitation increase into thermodynamic and dynamic components. And so basically we expect the change in TC precipitation overall, the kind of black term, can be split up into the change in moisture available, which is the thermodynamic change, plus the change in TC intensity, plus the change in TC size, which we call the dynamic factors. And so we kind of created this approximate breakdown based on partial derivatives. We estimate the different terms using a Poisson regression and then also some linear regression to estimate the changes in intensity and size with SST. And so here are the results from the RCE simulations of this breakdown. And so for the 99th percentile precipitation, we found that the total change in TC precipitation was about 8.6% per Kelvin, with about 67% of that coming from the thermodynamic contribution, 20% from the intensity change, and 2% from the size contribution. So size contribution was fairly small for the 99th percentile. If instead you do the area accumulated precipitation instead of the 99th percentile, you get about a 6.6% increase per degree Kelvin. The thermodynamic contribution is again the largest, with about a 12% contribution from intensity increase and a slightly larger 6% contribution from a size increase. And so to sum up, in these CAM RCE aquaplanet simulations, we found that warmer sea surface temperatures lead to less TCs overall. On average, the TC is more intense and larger. There are more extreme precipitation rates within the TCs, and more rainfall is coming from these extreme rates. When we did that breakdown into the thermodynamic versus dynamic components, we found that the results slightly depended on the precipitation metric you're looking at. But overall, the increase in precipitation was around the Clausius-Clapeyron rate, with the thermodynamic contributions dominating at about 2/3 or over as far as percentage. And also that outer size increases contributed more to accumulated precipitation, which makes sense, as you'd expect a larger storm to have greater accumulated precipitation. And so now my current work, which I'm just going to mention briefly, is linking these idealized model simulations to like AMIP style simulations, and then also to observations, and ultimately trying to understand what these idealized simulations can tell us about the TC precipitation response to real world climate change. And so pretty much everything I presented today is in this publication from late last year. The data from this publication is also available on the Dryad digital repository if you want to use any of this data. And if we don't have time for questions now, you can feel free to put them in the chat, or email me here. Thank you everyone for listening.
Yeah, thanks, Alyssa. I think we do have time for one or two questions. Brian has a question.
Just a point of clarification, the rotation they were adding to these RCE, that's like it's like Kevin's old paper with Dan about where they use a constant rotation everywhere, right? It's not a real rotation, it's an F-plane approximation.
No, so it's actually, no, it's not an F-plane approximation. It's like I make the omega of the simulation what the real omega is on Earth.
Oh, okay.
So yeah, so it's not an F-plane.
And you still get the accumulation of those long-lived vortices at the poles. They don't run into each other at the top.
They do run into each other. So let me just maybe go back if I can. So I think from what I remember, when Kevin and Dan did the F-plane simulations, the storms kind of didn't accumulate. They kind of went wherever they wanted to. Whereas when you add the full change in rotation with latitude, that's what causes beta drift. And so then the storms will drift poleward and westward and accumulate up near the poles. Yeah.
Okay, I was getting it backwards. Thank you.
No problem.
All right, so I had a quick question. Something you hear once in a while is that translation speed is also changing with climate. Is this something you can address in this configuration, or it sounds maybe like you can't? But.
Yeah, I could look at it. I think I did briefly look at it once, and I actually think I found an increase in translation speed with SST, like a slight one. Okay. But I just don't think it would be very applicable to the real world, just because there aren't other like these simulations have kind of very low shear and like other things that TCs in the real world normally interact with. Like the large scale circulation is just very different, so I'm not sure it would be applicable, unfortunately. Yeah.
Thanks.
No problem.
Okay. Thank you again, Alyssa. I think we'll now move on to our next talk on comparing CSM and WRF over South America, and the speaker's Patrick Callahan. So take it away, Patrick.
Okay, there we go. Okay, so first up, this is work that's supported from CAM7 funding from NSF, and we're going to be doing high resolution comparisons with WRF and CSM. So it's part of a collaborative effort focused on water and energy cycle in South America that's coordinated through the South America Affinity Group, whose website is at the bottom there. Currently, there are completed 3 one-year simulations for each phase of ENSO in years 2010 to 15 and to 18 or 2018. And there's a 20-year simulation that is currently underway at this time. And so there's a 4-kilometer WRF domain shown on the right here, and it utilizes 60 vertical levels up to 10 millibar or 10 hectopascal top. So using this refinement region, we created a hierarchy of regional grids with resolutions from 100 kilometers, which is no refinement, and down to 6 kilometer. And so each of these grids has a global base resolution of 100 kilometers. And for each horizontal grid, there are 2 vertical resolutions. There's the default 32 cam configuration. And then there's a 70-layer configuration in which the lowest about 38 levels are nominally aligned with the WRF levels, and the remaining levels are stretched to maintain the default cam model top. And for consistency with the WRF regional model, the boundary conditions outside of the refinement region are imposed by strong nudging towards ERA 5. So our approach in doing these simulations is closely follows the gray zone project to explore behavior of horizontal scales where large-scale tropospheric processes assumptions are no longer valid or are only partially applicable. And so for each ENSO phase, we'll have some 20 simulations with combinations of horizontal, vertical resolutions and deep convection options. And but rather than the focused case study approach of the gray zone project, we use a different approach where we use the contemporaneous results from WRF simulations at the 4-kilometer convective resolving grid as our version of the truth. And now, we're of course taking one model and kind of tuning it to another model, but there are other members within the South American group that are focused on the intercomparisons with observations, that we want to tie it down to both of these down to type of observations. So the grids in the refined region are aligned to allow future implementation of spectral methods, with each lower resolution grid being comprised of a 2x2 region of higher resolution elements. But for now, in order to compare the 4-kilometer WRF results with each lower resolution, we're just simply doing an interpolation with the conservative ESMF. So the results I'll show here are preliminary results using the 32 level configuration with horizontal resolutions from 100 kilometers down to only 12 kilometers. And for each of these grid resolutions, the WRF results were interpolated horizontally, but they still remain on the 60 ADA levels from WRF. And so that we're going to do comparative comparisons at the 2-kilometer and half-kilometer levels, which are made by selecting the levels for each of these models that are closest to those heights above the surface. So the upscaled WRF results here at each resolution represent nominally the idealized results we would like CSM model to to recover. And so in particular, this we're going to focus on the monthly mean values in the mean diurnal cycle for November of 2010. So so if you look here, this is a 100-kilometer resolution of WRF on the right and CSM on the left of the mean precipitation and 2-kilometer circulation maps. And so we want to look at how well CSM represents the South American low-level jet, which is commonly referred to as the Soleil. And also look at how does the pattern of precipitation vary with resolution. So we see here at the lowest resolution, we have this anomalous precipitation over the Andes Ridge in CSM, and whereas WRF is doing a much better job of representing the reality. So as the resolution increases, we see that the horizontal extent of this jet decreases. There's my mouse. So this jet here will become more compact and intensify along the face of the ridge, in contrast with WRF, where the jet kind of comes in here and then just sort of dies off. And so, yeah, and so we see also here, one significant difference here is in the WRF simulation, the intensity of the trade winds systematically decrease across the Amazon basin, whereas for CSM, the winds flow unhindered across the Amazon here. And as the resolution increases, we see that the precipitation, starts to resemble WRF better in CSM. And so this is just a summary of those results. And one other thing is that there's a halo of kind of non-precipitation in CSM seems to coincide with this this very high speed jet that's evident in the model. So to get a better view of the Soleil and the flow across the Amazon, we sample values along a profile perpendicular to the ridge and a profile lined parallel to the 2-kilometer winds across the Amazon basin. So for these figures, the colors below the profile of the surface topography indicate the mean precipitation rate. The upslope winds are represented by vectors, and there's little faint lines in there that kind of give it an indication of the model surface levels. And for each of these, the color contours will either represent the cross slope winds or the specific humidity. So, so we see here as this is a comparison of the two at the different resolutions. So we see that the upslope flow decreases with resolution. As the upslope flow decreases with resolution, the intensity and size of the jet increases. So you can see this here, that this by the time it's at 12 kilometers, the jet is like, much stronger, much larger. And also as the slope of the ridge increases with resolution, the upslope flow decreases, reducing the intensity and the spatial scale of precipitation. And by 12 kilometers, the precipitation is concentrated more on the face of the Andes here. And for Wharf, the precipitation, on the other hand, is more intense at the base of the ridge, where the specific humidity is higher than for CSM. So the upslope flow on the east face of the Andes acts to moisten the atmosphere above the ridge, while drying out the lower atmosphere at the base relative to Wharf. And we see also there's, associated with this excess moisture is significant precipitation. So if we look at an animation of the diurnal, mean diurnal cycle, we can see the undulations of the jet positions and amplitudes for Wharf and CSM. With the the Wharf jet is well away from the ridge, and the CSM jet is like right up against the face of the ridge. And we see with the relation from these, we see the relation between the variations of water vapor and precipitation values associated with this upslope variation. So the diurnal variations of profiles at the 2 kilometer level provide an insight to the pathology of the anomalous precipitation. Shown here are time versus profile distance, and the position of the ridge is indicated with faint vertical lines here, with cross slope winds, specific humidity, and corresponding precipitation shown. The 50 kilometer resolution provides the best view of the diurnal variations. We see there's an increased upslope flow starting here at about 16 Z, and that's followed by an infusion of water vapor over the ridge at about 20 Z, and that results in an intense precipitation event, centered around 2 Z that lasts throughout almost the entire day. And as the resolution increases, we see that the jet is better confined to the Amazon basin. The infusion of the water vapor is decreased, and the precipitation better resembles the results from Wharf. And you can see here also that there's the for Wharf, the Amazon basin has much higher water content. So a while back, Julio devised a diagnostic to suppress the convective circulation over the ridge by scaling the latent heat values to 0 over the topography. And so we repeated that experiment here for the 50 kilometer resolution. And we kind of note here the impact on the circulation over the Amazon basin here. So we get rid of the precipitation problem over the ridge by design. We see here that the intense kind of flow of the trade winds across the Amazon is actually reduced significantly. So to some extent, this convective circulation is drawing that air in and pulling it towards the ridge. If we look at the diurnal variations for this test, we see that the water vapor values at the base of the Andes better resemble that of Wharf. The diurnal impulses of cross slope winds at the lowest levels that migrate up the face of the ridge here, and there's an associated diurnal variation of water vapor that appears to feed excess values over the top of the ridge. So this kind of diurnal pulse propagates water vapor over the ridge here. And so we see here also that the Soleil is still too strong. It's further from the ridge, but it's not as far away as the Wharf result. And we also see that the maximum of the jet is now closer to the surface. So the Soleil is still too strong and too close to the ridge, and the question is why. notice, I don't have time to go into the profiles over the Amazon, but basically there's a systematic damping of the flow across the Amazon basin associated with the diurnal convection in WRF, whereas for CSM, that flow just flows unimpeded across the Amazon. So the hypothesis is that the undamped trade winds over in CSM are helping to fuel this problem and putting that jet too close to the ridge where it can be drawn in and through the convective circulation amplify and lead to runaway precipitation. So currently developing a diagnostic test where from the WRF results we want to derive an empirical damping function as a function of space and time, and then generalize the nudging interface to apply that empirical constraint from these computed values at each hour, and then feed that into the as an input to the model, and then evaluate the impact on the trade winds over the Amazon and orographic precipitation. So the goal here is to have two diagnostic tools where we can kind of get a handle on this and try and get a circulation that resembles WRF, and then kind of get to the bottom of the mechanisms that are leading to this this anomalous behavior. So this is just preliminary results of this hierarchy of these simulations. Have given us some useful insights already into the pathology of the erroneous precipitation over the Andes, and also the variations of model behavior as a function of horizontal resolution. And so once complete, these simulations will be an invaluable resource for model development. And for more information, as the simulation results become available, folks can visit the South American Affinity Group website and find out the status. And with that, I thank you.
Thanks, Patrick. That's a nice analysis. We might have time for one quick question. We're running a little late. Okay, so my impression is that the low-level jet in WRF is a lot further and less intense than it is in CSM at all resolutions. Is that correct?
That's correct, yes.
Okay, and so we don't know why. Okay. All right, well, thank you, Patrick. I think we'll move on now to the next talk, another variable mesh.
Yes, I'll share the screen. Does everybody can see my presentation?
Yeah.
Okay, then I will go ahead. Yeah, thanks for the opportunity to join this meeting. In this presentation, I will present the main outcomes of our joint atmosphere and land ice model working group project about applying VRCSM in high mountain Asia. And one of the main aims of this project is to find out whether VRCSM is able to simulate surface mass balance over glaciers in high mountain Asia. I did this project mainly over the last 2 years together with Adam, Bill, Gunther, Bill, and my boss, Sunil Am. Yeah, this is a short introduction to the high mountain Asian VR7 grid. So this grid has a regional refinement up to 7 kilometers over the high mountain Asia domain, which is actually necessary to have a high resolution in order to have an improved ability to capture the topographic variability over high mountain Asia, and also to improve the ability to capture glaciers in high mountain Asia. So this grid is
The cost is quite high, though. It's about 90,000 core hours per simulated year. And the model throughput is about 0.3 simulated year per actual day, running, using about 44 nodes on Cheyenne. Some key facts about the model setup. We applied a CESM-2 with an active atmosphere land surface components, namely the CAM6 spectral element die-core, further CLM5, and a diagnostic community ice sheet model, which means the ice is not evolving on the background, but we are still able to pass through a surface mass balance maybe in the future if there's a CESM grid. Further, an interesting feature is that we use elevation downscaling scheme, but with 36 200-meter interval elevation classes up to 10,000 meter altitude. The next step, of course, is to develop the topography and land surface data sets. I will only show you the topography because it's quite interesting to see that the high mountain Asia topography has a more accurate representation compared to the globally uniform 1 degree and 0.25 spectral element grids. This is a snapshot over in the western part of high mountain Asia, mainly the Karakoram region. And as you can see, the blue line, which is nice, meandering, so to say, is the upper Indus Valley. And it is also already quite good visible in the high mountain Asia topography. We did two different kind of simulations. The first simulation where we started like 2 years ago is we only applied one spin up year. Mainly the default of the settings were all default in CESM-2, but the only thing we changed is that we decreased the maximum snow depth from the 10 meter in CESM-2 back to 1 meter in CESM-1. Mainly because we think 10 meter is a bit too much for high mountain Asia, but also that if we only have one spin up year, that would not be sufficient enough to get to the 10 meters water equivalent. However, after the first simulation, we found out that the surface mass balance was underestimated, so that was reason to do a second simulation with a more thorough spin up approach with 10 years spin up for the atmospheric component and 50 years spin up for the land surface component. We increased the maximum snow depth in order to allow for higher refreezing capacity. We increased the ice albedo so we could lower the amount of ice melt. We turned off the long wave downscaling because did not do a really good job, especially in the lower altitude, so to say. And further, we applied a different rain snow temperature thresholds that are more in line with the observations over high mountain Asia. We applied some tunings on cloud cover and sea ice, including the Morrison-Gettleman 3 cloud microphysics scheme and an updated glacier cover dataset. The outputs are all evaluated, comparing it with gridded outputs from the globally uniform CSM grids, the reanalysis satellite-derived products such as the watch forcing data ERA interim, JRA55, and MODIS, and also RCM-based outcomes from WRF-based glacier model. Now time for the results. So some of the main outcomes we have learned that if we are looking at the 2 meter temperature, is that there are warm biases, in particular over the Eastern Tibetan Plateau, which is region number 4, that's the gray region, so to say, during the summertime. We see also that with the increasing resolution, that the warm biases become slightly smaller. However, over the mountain ranges in the western part of the high mountain Asia, so mainly region number 1, but also a bit region number 2, so really the mountainous regions, we see a cold bias, and the cold bias becomes larger with an increasing resolution, and it's actually a more common problem with models when resolution is increasing, so to say. If we look into the precipitation variables, we see that the rainfall, mainly in the southern monsoon-dominated regions, that they are overestimated. But still, the high mountain Asia grid is doing better than the globally uniform 1/4 degree grid, a bit comparable with the 1 degree grid. Though, and the snowfall is mainly overestimated in the western part of high mountain Asia, which is linked to the cold bias, and also to some extent to the changed rain snow repartitioning in the second simulation. If we look into the snow cover and the snow depth, we see that the snow cover is overestimated and slightly underestimated during winter and summer respectively. The high mountain Asia simulation shows some improvement compared to the coarser CSM grids, and the best match can be seen over the autumn period, where the bias is more or less it's actually doing showing a good result. Compared to the JRA 55, which is one of the better data sets in terms of snow depth over high mountain Asia, we see that the snow depth is mainly overestimated in the western part of high mountain Asia, which is of course partly attributable to the cold bias, but also to some extent to the snow model modifications, which also include the higher maximum snow depth. What is it all about? We want to know whether the model is able to do a good reasonable job in simulating surface mass balance. And as already mentioned, we found out that after the first simulation, that the surface mass balance was underestimated, which is the gray line over here. The modifications we did for the second simulation did a good job, though, in improving the results and reducing the surface mass balance bias, especially in particular in the region number 2, which is the Southeast Asia, the monsoon-dominated region. But still, there's still some considerable space for improvement to close the gap. However, we see at least that the amount of grid cells at the end of a run, where a positive surface mass balance is simulated, that it triples. And if we look to the spatial differences, we see that in particular in the southeastern part of high mountain Asia, we see a good improvement of the surface mass balance, which is most likely attributed to the updated glacier cover dataset, because the reason to update the glacier cover dataset was that we found some inconsistencies, mainly in the southeastern part. So it looked like it's doing a good job. And I think also mainly in the higher regions, the higher altitudes, we also see a better job because the former glacier cover dataset was only limited to 6,000 meter altitude, whereas the newer glacier cover dataset is limited to 7,000 meter altitude, so it captures most glaciers. But still, the question here is why is this bias there, and what can be partly the reason for that? So first of all, we think that the warm temperature bias of Central Asia, particularly over the Tibetan Plateau, but also the cloud cover bias, which is a negative, so an underestimation of cloud cover over high mountain Asia, can contribute to this negative surface mass balance bias. A potential solution to solve this could be to nudge CAM with ERA interim or ERA 5. Further, there's some missing physics that are not there. For example, solar radiation downscaling that takes into account the hill slope aspect and orientation, which could be relevant for the northward oriented glaciers in the region. There is no precipitation downscaling. We did not include debris cover, and also avalanching is not included. That is in fact an important accumulation term for mountain glaciers. Now, the last point would be the elevation downscaling of in CLM. In the current setup, elevation downscaling is only applied to the glaciarized land units, but ideally it should be applied to the entire grid cell. And one reason for this is that if the community land model is doing its calculations, that eventually a grid cell mean is communicated to the community atmosphere model. And this grid cell mean is actually a product based on its underlying land unit distribution. And in case, for example, we have a grid cell where vegetated fraction is quite large compared to a glaciarized fraction, the glaciers, then eventually the vegetated land fraction is dominating the signal of the grid cell mean. And by its interaction between CLM and CAM, there is a likeliness that that eventually this vegetated land fraction influences the glaciarized land fraction in a negative way. And for this reason, it will be ideal if elevation downscaling is applied for the entire grid cell, so to say. And one small, I put one small graph here to demonstrate it a bit. I selected here all the grid cells in a around 5,000 meter altitude. So to have a bit same altitudes, so to say. And what we see is that that if I lower the glacier fraction of it, the glacier fraction is lower, we also see a more negative surface mass balance. So it could be kind of related to that. So there is more improvement needed in the interaction between community land model and the community atmosphere model. That brings me to the conclusions. We see temperature and precipitation biases, but also improvements compared to the coarser CSM grids. Relative to the snow cover observations, the high mountain Asia grid shows a better agreement. And the snow depth, we see that it's mainly overestimated in the western high mountain Asia region, where the first simulation is showing a slightly better agreement than the second simulation, most likely due to the snow model modifications. And further, the high mountain Asia grid can simulate a positive surface mass balance, but is underestimated. We see that the performance is is improving with the second simulation, but there are still some work on the road for future applications that hopefully will reduce the surface mass balance bias further. That was actually my presentation. Thanks. Are there any questions?
Thank you, Renee. I think there's a question in the chat from Ji Hong. In the interest of time, we're running a little late. I'm going to ask you to just address it in the chat, and I think we'll move on to the next talk, and we'll have some time for discussion after this last talk.
Yeah, thank you.
Okay, thank you. So the last talk in the session, and the last talk of the meeting actually, is
on thermospheric and ionospheric gravity waves by Han-Li Liu. And I see your slides, Han-Li, so why don't you go ahead?
Okay, can you hear me? Somehow I lost control of the panel.
I can hear you, and you're not in full screen mode, but
okay, let me try to adjust that. Is it?
There you go.
Okay, all right. So here we're going to look at the thermosphere ionosphere effects by gravity waves from the lower atmosphere. And I first want to thank my co-authors, Peter Lorenzen, Francis Witt, and Steve Goldhaber. So here's the outline of the talk. I'll give a very brief description of the model. And for the analysis, we'll look at the spatial distribution and also local time variance of the resolved waves. And also look at the wave forcing and their impact on the thermosphere circulation. We'll look at the scale dependence of wave power and momentum flux. Just see which waves are contributing more to the power and momentum flux. And also we're looking at the ionosphere and thermosphere perturbations caused by gravity waves. So as Andrew mentioned, this is part of the CEMA effort. One of the things we've been doing last year is to develop the species-dependent spectral element dicore, and we're running with CESM transport. Also, for the thermosphere, the molecular viscosity and diffusion are critical, so they have been added in both the horizontal and vertical direction. And like previous version of WACMX, we have interactive chemistry, dynamo, transport, and energetics. And we have built a regrading scheme to kind of mediate the communication between physics mesh and the geomagnetic grid. So here are some information on the model configuration. And we've been running with two different resolutions, the lower resolution NE16, about 2 degrees, and with 130 levels, and then the higher resolution NE120 with 273 levels. And here on the right is a plot showing the vertical resolution in terms of scale height. And you can see that for the high resolution configuration, in the middle atmosphere and most of the upper atmosphere, we're using 1/10 of a scale height and transition to a quarter scale height resolution near the very top. And this is because at that altitude, according to our test, most of the waves with shorter vertical wavelengths have been damped out. And one thing I want to mention is that for the high vertical resolution or high resolution simulation, we have turned off the gravity wave parameterization. And so this shows the spatial distribution of wave activities at 4 different levels in the, right above the tropopause in the lower stratosphere, upper stratosphere, lower thermosphere, and upper thermosphere. So this is in terms of standard deviation of temperature. And at this level, at the lower stratosphere, you can see the kind of a few hotspots related to the deep convection in the tropical region, and also orography, Rockies and Tibetan Plateau. And then when you get to the stratosphere, upper stratosphere, in the convective generated waves are still there. The band shifts a little bit to the south, probably due to the wind system and also the propagation of the waves. But the orographic waves are mostly gone. Even though the mean wind doesn't have any critical layer, doesn't have a zero wind, we do have a very large stationary wave 1, and which does produce this critical layer filtering for most of the orographic waves. So most of the activities by then you can see it's poleward of 45 degrees, so mid-high latitude, and seems they're not related to lower atmosphere or troposphere sources, but rather more related to the adjustment of the stratosphere jet. And in the lower thermosphere, we can see that the wave sources or distribution become more uniform, and likely due to the propagation of the wave and also the further shift, southward shift of this band. And this is, as I will show later, this is consistent with what we have seen in observations. And in the northern hemisphere, you still see the signature of the waves, which you have seen in the stratosphere, but more uniform again. And in the upper thermosphere, we see again the two bands, signature of the two bands at higher latitudes, and which are likely from this sources here, as we show in the lower thermosphere. But the largest activity are found near the two geomagnetic poles. And there are middle atmosphere gravity wave observations. This one is from SABRE for January. And here, just to point out the nice correspondence, at least to the first order, of the wave activities from the observation and from the simulation. So here we see this band of activity extending from North America to across the North Atlantic to western part of Europe. And you do see that signature here. And also eastern part of Australia, over the Pacific, and east of Brazil, and east of Africa. So all these activity spots seems to be captured by the model. And there are not a whole lot of thermosphere gravity wave observations. So here's one of them from the Gochi satellite measurement. They measure the relative density and zonal wind. And the general impression is that they have low activity at low latitude and increasing activity to the poles. And also they show this very strong activity around the geomagnetic pole, and which both features seems to be captured by the model, the two bands, and then the activity center here. This one is a little bit busy, but the point here is trying to show the time dependence. So we're showing here 4 UT times every 6 hours, and then the daily average at 3 different levels. And we can see lower down, there's not much local time dependence of the wave strength. And as you go to higher altitude, because of the more dominating tides, you do see more and more stronger local time dependence, and also day-night difference. And particular, if we look at in the thermosphere, we see this kind of activity centers attached to the westward wind face of the wind system, the zonal wind, and that's usually around the early morning. So this is a very clear dependence, and the waves usually propagate against the mean flow. So so here we are seeing mostly the dominant wave is the eastward propagating waves. And the other thing from this comparison is that we do not see we do not always see the hotspots being at the same spot. They may vary with altitude. And this is the vertical structure of the gravity wave from, again, this is from SABRE, latitude and height. And the 2 features I want to point out. One is this poleward shift of the activity center as you go to higher altitude in the summer hemisphere. And then in the northern hemisphere, the winter, you see this activity mainly above the stratosphere jet core. And that feature was reproduced in the earlier Wacom simulation. This is with a similar resolution, but it's only goes up to the lower thermosphere. And then in the new Wacom X simulation, we are able to see similar features. Another thing is if we look at the wave activity further upward, we see that the waves, gravity waves, make it well into the thermosphere. And here with a peak at around 150 kilometers. And that's a region where it can strongly modify the dynamo process. And when these waves go into the thermosphere, they may generate deposited momentum, which has not been characterized before in using the parameterization in the coarser resolution models. So here we can look at the forcing, both the zonal mean, zonal forcing, and meridional forcing for January. And we can see that they are very significant on the order of over 100 meters per second per day, and larger in the northern winter hemisphere. And both hemispheres, they are eastward. For the meridional wind, they are always southward against the summer to winter circulation. So, one thing we know is that with eastward zonal forcing, that will generate equatorward Coriolis force. So in the northern hemisphere, the zonal forcing and the meridional forcing kind of reinforce each other and slow down the slow down the circulation, meridional circulation. And opposite in the other hemisphere where they offset each other. And here we compare the higher resolution model and the coarser resolution model. And indeed, we see that this is the mean meridional wind. We see the weakening of the in the northern hemisphere, and also in the vertical descent, downwelling also weakened by the gravity wave. And in the other hemisphere, the southern hemisphere, actually seems the Coriolis force went out and have a strengthening of the mean circulation. And this have important implications for the thermosphere composition. One of the key quantities in the thermosphere measuring the composition is the ratio between the atomic species, the major atomic species, atomic oxygen, and the major molecular species, N2. And in previous modeling studies, WACAMX, and also in TGCM, we see that the O2N2 ratio is often overestimated compared with observations. And that's the case here. If we look at the NE16 model, we see a very large O2N2 ratio, especially in the winter hemisphere. And then with the reduction of the meridional circulation, that downwelling, which brings down the atomic oxygen poor atmosphere from higher atmosphere, from higher up, that was reduced. So as a result, the O2N2 ratio is also reduced. And you can see that from the zonal mean value going from 2.5 to 1.6, which is a significant improvement. And also, if you look at other important minor species or neutral and also ion species, they are also affected by the circulation change. And this is to quickly look at the scale dependence of the wave power and the momentum flux. This is for larger scale waves, 300 to 2000 kilometer, and this is from the smaller scale. So we can see that for the energy density, the large scale waves do play a more important role, but it's a different story for the momentum flux. For the momentum budget, we see that in the middle atmosphere, mid-high latitude, it's dominating. And that's exactly why we need a parameterization to get this part right, because they're missing. And even in the thermosphere, they can still play a very important role, up to 60, 70%. And it should note that in the model, the parts from 30 to 200 kilometer, they are under-resolved or not resolved, and they have to be estimated here. So that's the, and then the TEC, the total electron content, is also disturbed by the lower atmosphere waves. Here we show one specific UT time, one frame from the animation Andrew showed. And this is the daytime and this is the nighttime. So this is the terminator. And you can see that the perturbation is on the order of about 3% plus minus. And that is in general agreement with available ground-based measurement during geomagnetic quiet times. And also we found that they seem to show very strong local time dependence. And if we overlay some schematic, wind, averaging wind plot, we see that they are, most of the time they are propagating against the wind, the dominating large-scale wind. And also one particular feature I found interesting is that at the nighttime, you see this against the wind. You always see this southwestward propagation of the TID or the waves, and this has been interpreted before as probably due to Perkins instability in the ionosphere. But our modeling result shows that the lower atmosphere wave may play a very important role in causing those propagations. So I think I will just stop here and put a summary up here and take questions.
Okay, thank you, Han-Lee. Are there, Lynn Harvey has a question. Do you want to go ahead and ask it, Lynn?
Sorry, I couldn't find the mute button.
Sure.
Yeah, I just wondered what the sources were for the thermospheric gravity waves located at the geomagnetic poles.
Yeah, because if you look at the lower altitude, you don't really see a peak there. So my hypothesis is just the wave sources may be still uniform, but near the geomagnetic pole, especially for waves with very slanted or vertical kind of phase propagating phase lines, they may experience a less of ion drag. So it may be an ion drag effect, less ion drag near the geomagnetic poles. But we need to test that. So we're still looking at that.
Okay, thanks.
All right. So at this point, we have maybe 8 to 10 minutes for discussion on the talks in this session. I'd just like to open it up to anybody who would like to ask any of the speakers questions on their talk, or bring up any issues that you'd like to discuss related to high resolution modeling. So Han-Lee, would you?
Yeah, I don't see that's the problem. I don't see the control panel. Where have they gone? Usually you move your mouse to the top.
Yeah.
Oh, now I see. Okay, it's on the other screen. Sorry.
Okay. All right.
If nobody has anything, I have a question for the group or Han-Lee.
Please go.
So I gave a talk yesterday that focused on the easterly wind bias in Wacom in the polar upper mesosphere in the wintertime. And Han-Lee, it looked like that was kind of missing in your runs. It looks like you've got westerlies that extend, I mean, they weaken, but they extend all the way up into the thermosphere. Is that because you're resolving higher order gravity waves with the higher spatial resolution?
Yeah, yes. Let me, maybe I can quickly share one backup slide here. Now, finally, I think I found the control now. Okay. Let me see. So maybe you are talking about this one. I have a backup slide here. Maybe what you're talking about is this in the in the MLT region, the wind reversal in parameterized runs, you always see a very strong reversal in both north-south hemisphere or winter-summer hemisphere. But in reality, when you see the observations or climatology, you see very weak westward reversal, and it doesn't extend all the way. And they are at different altitude. And it seems that feature is being captured by this high resolution model, even though the reversal strength is still weaker. Maybe, I'm sure we're still missing waves, but qualitatively, we are getting the right reversal at the right altitude, and even the latitudinal extent of the westward reversal in the winter hemisphere. Is that what you're?
Yeah, that's really exciting.
Yes, I'm happy to see that too. I actually, Nick mentioned that yesterday.
So Han-Li, I'm not sure I read this correctly, but in your NE120 runs, you're not using any parameterized gravity waves?
Right, we have turned off all the parameterized gravity waves.
Hi, Han-Li, this is Valery. Is it non-hydrostatic or hydrostatic version of the model?
The current SE is hydrostatic.
Hydrostatic. And do you have any special arrangement near the top model for high resolution?
On the top,
dissipation or something like.
Oh yeah, that's right. We do have increased hyperdiffusion at the model near the model top.
Okay, thank you.
I think Joan asked you a question in the chat.
Yes. Oh, in the chat.
Hi, Han-Li. Yeah. Hi, Han-Li.
Hi, Joan.
I asked, when I just kind of watched your presentation, it seemed like the waves that you see in the thermosphere are mostly evolving because of wave filtering effects. And maybe that's not a correct impression, but that's kind of what it looked like. And I just wondered if this high resolution configuration could capture any secondary wave generation, if it's capable of doing that.
Yes, it should be. Although I think it's kind of challenging to separate the primary and the secondary waves, but we do see a kind of a signature of the secondary generation. Especially, I mean, this one is, I haven't looked at this one yet, but in the earlier Wacom simulation, we have run for July, and we see that, lower down over the Andes, southern Andes, you see a very typical kind of wave structure from the mountains. But then when you go to higher altitude, at above certain altitude, that kind of the planetary waves start to give way to this quasi-concentric waves. So I think that's an indication, as Eric and Sharon's paper showed, that's an indication of secondary wave generation after the breaking of the primary waves.
Okay, thanks.
I see there's been some discussion on Renee's talk. I don't know if it's been dealt with to everyone's satisfaction. Thomas, did you want to raise the issue about the mid-latitude jet?
Yeah, it's a curiosity I have, and I simply don't know. Maybe some of you guys have already clear answer about this. But if you refine the grid in the middle of the mid-latitude jet, would you expect some effects on the jet itself just from that grid refinement? Open question to everyone, maybe.
Yeah, so I can just offer a quick kind of thought on that. So we have done a decent number of simulations where we've refined over like North America or the continental United States. We have looked at kind of like the upper level U200 kind of fields in this. We actually haven't seen a significant sensitivity in the jet magnitude. I've always kind of interpreted that as, the synoptic scales are relatively well resolved at 1 degree. So even if you push it to higher resolution, we don't really expect to tighten those gradients at all. The one area where we may be seeing some changes is if you refine over a mountain range. So this would be one potential thing to consider with the Himalayas, is you can kind of modulate that flow that goes over. And then, you have all sorts of, PV conservation, and, you can kind of get all these interesting Rossby wave effects. That, I think, is probably the place we'd see more of the effects of regional refinement on the upper level jet itself. But that's just speculation on my part.
We have seen this when we've done refinement over the United States, or even over a particular region. When you refine, even in some kind of held Suarez case, you refine over a region with a wave, and then downstream you will see impacts. But as Colin was saying, it doesn't really affect the mean, but you do get nonlinear or higher frequency wave interactions that do affect the overall circulation. It's not, we haven't seen it as being systematic, but it is there, and it tends to look more like a uniform high res. So it does sort of do the right thing with the unresolved scales.
Thanks.
So Owen has a question.
Oh, I didn't see that.
I just popped up to earthworks, but also general. Can one imagine a systematic way of simplifying, making physics faster? Have a 3 kilometer version with all in, and then make the physics faster, or test at lower resolution and remove? I don't know. What I showed yesterday, we put the whole thing on GPUs and we'll get a factor of 3 to 10. I mean, the physics is parallel, and the GPUs have a lot more cores available, so we can get the same, we can actually do better that way. Simplified physics, I mean, we do simplify the physics in the sense that you get to 3.5 kilometers, you're not going to have a gravity wave parameter, or sorry, you may lose some of the gravity wave parameterizations, and you may also lose the deep convection, which are not super costly, but you're still going to need, you need microphysics, and you need moist turbulence all the way down is the problem.
Let me give a specific example. Let's say if we could run the first 2 decades with the prognostic aerosols, but then later on we can do more general aerosols, because then greenhouse gases is the more dominant. Would that make the model? Would that make too much work compared to having enough speed on GPUs?
It's a different model. It's not the same model. Once you start changing the physics that much, you don't have the same set of parameterizations, and interactive aerosols do actually, change cloud feedbacks, for example.
Yeah, certainly. So I'm always been a fan of putting in as processes as possible myself, but I know then going down.
I mean, you can make the argument of calculating an offline aerosol and then putting that back in, as many people do. So there are ways of doing that, and for some smaller scale things, you could run without aerosols, or using them as boundary conditions. But for climate purposes, when we have to run long, I don't see being able to change the physics. I think the big thing that we're potentially going to be doing is, earthworks is aiming at uniform high resolution, but everything else we've seen here is variable resolution. Usually when you're asking a high resolution question, you're not asking it over the whole planet in every regime. And so the way I think we're going to get the speed up is to do the 3.5 kilometers over one particular region of interest, whether it's the United States or Europe or a tropical cyclone basin or South America, as we've seen. And that's how we're going to make the model faster. We're going to ask specific problems, not every problem. Because 3.5 kilometers over a region the size of half of North America or the EU or the Amazon, we can run today for climate purposes if we're doing a couple.
Then I have 2 different models as well. I mean, the properties of a refined model in
they're not, but as we've seen, the dynamics are actually fairly well constrained. Yes, there are some details, and we're working on physics that seems to work. I mean, what I showed is that the CAM6 physics, it gives you a different answer, obviously, say over the Western United States with orographic precipitation, but it gives you kind of the correct answer. And
but like the global radiative balance, is that the same?
Well, the beauty of doing refined resolution is the global radiation balance is 95% the non-refined region. What we found is it's easier to tune a refined mesh coupled model because most of the planet is low resolution and performs that way. So you keep the energy balance, and then, okay, if your energy balance is off over part of North America, it really is not going to affect the whole coupled simulation because there's so much flux of energy in and out of the region.
Okay, yeah, okay. Then,
So I think there's actually big benefits to doing it that way. We don't have to tune up a 3.5 kilometer coupled model. We tune up 100 or 60 kilometer coupled model. You refine over one region and you still get the same energy balance because the refined region where you might screw it up is so small.
Okay, so that has been checked that it actually works that way. Okay, then it's fine.
Yeah, so this is actually in the regional paper we did in 2019 using 14 kilometer refined mesh over the US. We got a better simulation at 14. One of the reasons we got a better simulation at 14 kilometers than uniform high resolution 14 kilometers globally was that the overall energy balance of the planet was better because most of the planet was 100 kilometers, and we know how to do that.
Yeah. Okay.
All right.
Good.
This is a good discussion, but I would like at this point to have us go into breakout rooms. We're going to have, I think, 8 breakout rooms. There's no, there is not a real, well, let me put it this way. There's no assignment. People should, I'm going to put up a list of discussion topics that you might want to cover in your breakout group. If not, you don't have to. When I think we'll go for about 15 minutes, and when we're done, well, we will go for 15 minutes, and then people can. I have assigned rapporteurs for each group. We'll hear from them, and we'll have a discussion after that, and then we'll adjourn. So thanks to everybody, and I hope this works. So I'll stop sharing my screen now. Okay.
Everyone's been invited to join a room. You'll see the button at the bottom of your screen. And if you have any problems, just turn on your mic and let me know, and I can send you to the room of your choice.
So
Yes.
Are people going?
Yeah. Yeah.
Oh,
If you,
I didn't get an invite. I don't know.
there's a button at the bottom of your screen that'll say join breakout room.
Nope, I don't see one. Breakout rooms. Oh, so I have to pick one. I thought you were assigned them. Okay, got it.
No, we'll let you pick who you want to join.
Oh boy, which one has the cool kids?
If you open up your participant list,
they said they don't want me. They don't want me in the cool kids.
I thought we would do it at random, but okay.
Well, they get to pick, yeah. Just because Folio, it's easier when we've got some people assigned to lead the rooms. You can't have it both ways. Oh, Folio left. Peter, if you need me to send you to a room, I'm happy to help.
Trying to figure out which one to join. Rich seems pretty lonely. He's the only one. So maybe I'll join them.
Room 2.
Then we're just really talking to each other. I'm looking for like an outside person's room.
Well, they've all got at least one staff who volunteered to be the note takers.
Right,
so,
right.
Room 8 only has Rebecca and Simone.
I'm worried that's going to be very chemistry heavy.
Oh, sure.
I don't know. Anyway, I'll probably go to, looks like one's very popular. Oyvind's in room 2. Whoops. Let's see if this works.
So if anyone in the main room needs some help joining a breakout room, go ahead and let me know.
Elizabeth, I can't see what the different discussion topics are in the different rooms.
Each room is discussing the same list of topics. It's just a matter of who is leading the discussion and who's there to put their own twist on the conversation. So I can assign you randomly, or you can look at the breakout room list and see if there's someone in particular that you'd like to connect with.
You can assign me randomly. Thank you.
So now you'll see the button to join.
Thank you.
I sent you to room 5.
Thank you.
So Joan, you'll see a button that says join. Hi. Oh, you're muted. You're muted. You're muted.
Hi, Elizabeth.
Hi, I'm sorry to interrupt. How long do you want to give for the reports and what time should I just send everyone back to the main room?
How long have we been in?
Good question.
Why don't you give us till 2:30. Well, give us 4 minutes.
Will that be
More.
enough, do you think?
I think it'll be enough. We still want to have some discussion afterwards, so. Yeah.
Yeah.
All right.
Okay. Okay, that sounds good. I know that the agenda does say adjourn or later if necessary, so.
Well, it can't be too much later. I actually have to leave by around 5:03. So.
Okay, that
right.
sounds good. Yeah, so when you go back, I'll give everyone the 4-minute warning.
All right. Thank you.
Thank you. Thank you.
Okay. Has everybody has returned, it looks like. I thought we could just spend, maybe a minute if people want. If they don't want to, if a breakout doesn't want to report, then you don't have to. But I think it'd be useful just to hear at least some summary of what was discussed. So I'll just go in the. I'll go first, and then we'll just go from there. I think I have a list on my computer that seems sort of random, so we'll just go by that. I'll go first, then Brian, then Cecile, then Louisa, then Nick, Rich, and Simone. So in my session, there were some questions about running. Well, it was kind of a two-part question about high resolution, variable resolution simulations over large domains, in particular Africa. We were asked whether whether these things will be ready soon and whether they will be runnable on the cloud. I don't know if Brian is on at this point, but we spent a while talking about how to judge the cost of, how to assess the cost of these variable resolution simulations. It's brought up that it's not only the columns, although that certainly seems to be the most important factor. It's also the fact that with a given number of columns, the smaller the grid spacing is, the smaller the time step is. So there is a dependence both on grid step and number of columns. Then we spent, I had to leave for a bit, so I didn't hear the whole discussion, but it sounded like we were revisiting the whole question of physics, I don't know what to call it, ill-posedness or just non-convergence, that our physics, most of our physics in climate models doesn't satisfy, we're not sure at what point the answer will stop changing as we decrease time step, and also kind of related the vertical resolution. So those are the things we touched on. And why don't I'll just turn it over now to Brian.
Thanks, Julio. Yeah, my group started off with some general praise of several of the talks through the last few days, especially pointing out use of the hierarchy of models to look at how to improve the model by going up and down in ranges of complexity and looking at processes in detail. And then we talked a little bit about SEMA and seem to agree that unified modeling is a great idea. It's hard to do, and it's been wanted for a long time, and it's good to see some progress on that front. There was some question about whether everything that's in SEMA right now is really needed in SEMA, but that might be biases just on the part of the members of the group that we had. And then we turned, I turned the question onto die cores and whether or not the people in the group would be impacted if we dropped some die cores. Some of them didn't know that even Eulerian was still hanging around in the model, so it wouldn't be impacted by that. But there was quite a bit of discussion that if FV were to disappear suddenly, it would be problematic for a lot of groups, including for paleoclimate applications and other exotic applications, because at least the perception right now is that it would be difficult to set up new simulations in those kind of more exotic configurations for the SE or other die cores. Especially the lack of post-processing tools for irregular meshes is a major issue.
That's a good, interesting point. Okay, So then, Cecile.
Sorry. Yeah, then in our group, we talk a little bit about the new vertical resolution and the fact that the model was becoming more and more expensive. And the fact that NCAR has always the pressure of cutting edge simulation and resolution, but also that the community wants also cheaper version of the model that's not necessarily simpler model like Aquaplanet. They want a real model that they can run and give a climate with a full ocean model and land and everything. Then the question would be, in terms of software engineering, it would be probably easy to set everything that they can run at lower resolution, but the question was who would do the tuning? And would it be the community that sent back the tuning to us? It would be coming back that we had starting a tuning document that's a living document and it's still in progress. But the fact that it requires resources and where would these resources would be coming from if it was the community doing some of the tuning. And we talk also about the alternative that would be to provide as a set of simulation. NCAR would do simulation like CMIP simulation on large ensemble that we would provide back to the community. They were also about the cloud computing, the question that if we start to do more cloud computing, where the funding would be coming from, and nobody had really the answer in our group about this. And the last point that was raised, it was about diagnostic set, new set of diagnostic to analyze, run, and to compare to ops. And we say that we are working right now in a new framework. It was your last point, stuff that was not discussed in the meeting. And we asked the community to stay tuned, and we hope to have this coming soon. This is it.
Okay, thank you. So Luisa.
Mute. So one question was a desire to have a bit more clarity on which dynamical cores will really eventually be supported. And maybe that, sort of impossible question, but that would be helpful to users to know that they don't pick a dyna core that's not going to be supported, a few years down the road. And we also talked about the fact that we hadn't really talked about post-processing and the new diagnostics package at all in this workshop. And so that might be a good opportunity in June that we discuss those, the new ADF, Atmospheric Diagnostics Framework, and Melody's Monet, and show people where that stands. And it's also pointed out that Aerocom has some diagnostics package written in Python that we should probably check out and compare. And another final suggestion to compare our Musica results with the CAMS, the Copernicus European family of regional models, and they have a nice framework set up for model evaluation and observations. And that was it.
Thanks. Nick Davis.
All right, so our group focused a lot more on the model aspect a little bit. So we came up with the need for a better sort of generalized empirical constraint interface for the model, where you can do things like nudging and forcing experiments. Seems like a lot of folks now are starting to get into that in the community, and I think even internally it would help to have something robust and generalized to do that. We talked again about inline zonal mean capability that's dicore independent for a lot of things. Continuing to support some cheaper configurations, even in new dicores. For whole atmosphere, this would be something like the coarse resolution middle atmosphere setup. Things that support climate length runs, basically. Different ways to output average fields. So one that came up specifically for and I think it applies to both tropospheric chemistry and upper atmosphere chemistry is daytime versus nighttime averaging. And that's where the daytime average is at each point sort of local daytime average. So that carries probably a lot of very particular constraints on how exactly you do that. So it's a well-behaved field, but I think that that's something that sounds like there might be some demand now. And then just what additional mechanisms should exist for users to get computer time on NCAR machines. We talked about the value of containerized interface that allows folks to access the node locally. Debug queue, something that's low resource, like can't be too many nodes, but is extremely high priority when you just need to runtime test things, but you don't necessarily need to do an actual full length run. And then sort of musing about something that's the opposite of our NSC program, where it's small allocations with short time window allotments, so 6 months or less.
Okay.
And that may help entrain, university users who don't have an NSF grant, but also don't want to do a huge project. And that's all.
All right, thank you. So Nick Peditella.
So our group was all internal to NCAR, so it really only captured that perspective. And admittedly, we spent maybe the first 5-10 minutes of the breakout discussing science topics first. But we did discuss a bit about moving to GPU computing and trying to understand, what parts of the model really should be moved and would make sense to sort of put in the effort to port to a GPU and get a sufficient speed up that it would really be worthwhile from that perspective. And that's all from our group.
All right, thanks. So Rich.
Yeah, it's pretty much similar ground to other groups, but I think on the aspect of what should we have more simple or more complex models, and the answer is yes. But the idea, I think, in terms of knowing that we have to get rid of things ultimately, the most important thing is to say, what are the alternatives to you running T31? What are the alternative we're going to be able to give you is really important. And also, I hate to say this to a certain extent, but like, we need to know where, we are making decisions based on who is using the model for those particular applications. And so I think a survey at this point is probably, to stand behind when we do get rid of T31 or something, or the whole spectral core. That's a good idea. The other aspect was access to computing and different computing platforms. And someone pointed out that even though individual institutions have clusters, they're sometimes very hard to use, even though it's like free computing time compared to Cheyenne, but Cheyenne is very easy. And I think, it's a little immature at this point, but in terms of containerization and cloud computing, Brian Dobbins is working pretty hard on that here at NCAR. And I think the containerization is close to being, usable by people and testable by people in the kind of cluster environments. The cloud computing is definitely doable, but I think there are certainly some complexities about the way the infrastructure works in the cloud versus something like Cheyenne that needs to be overcome. But I know, the other experience with the tutorial, for example, that it is accessible for certain ways of running CAM, but not every way. And then the final thing was related to, having access to CPU hour cycles on Cheyenne, for example. And there are, Colin in our group mentioned there's 1 or 2 ways that people may not be aware of to get access to some computing time potentially that does not require NSF funding, because that's usually the big bridge to get over if you want access to more time.
Okay. Thanks. And last, Simone, do you?
Well, our group was small, so we decided to merge to Louisa's group, and that already got reported.
All right. Okay, thanks. So we have maybe 10 minutes for just a free-ranging discussion. If there is nothing anybody will, if nobody brings up anything, oh, Patrick has his hand raised.
Well, I was just going to follow up on that last point about the cloud computing options. I was just wondering if that would take the place of the small allocations problem to be able to do that sort of work in a cloud environment, and would alleviate that pressure. But I don't know who paid for it though.
Yeah, I'm very fuzzy on how the cloud gets paid for. I'm not the person to ask about that.
I can say the word that Brian done. We get credits from Amazon, Azure, and other providers, which help us do a lot of work. It's still expensive relatively. It's not as if they're running for the same kind of dollar cost or whatever you want to compare with Cheyenne. It's still quite expensive. And I think, but more the challenge is cloud GPUs, as soon as you start moving data around up and down to the cloud, that gets expensive. I think that's a big problem. And they're just not designed to run, distributed jobs like we want to run in the way that we want to run, but it's getting better, I think, from what Brian tells me.
So I was struck at, it seemed to come up very explicitly once and maybe twice, the idea that, yeah, the community wants cheaper configurations, but not, not just simple models. The community wants, a quote unquote real configuration that's cheaper to run. And that, I think that's an interesting thing to think about. My immediate reaction is, lower horizontal resolution or CAM4 physics. I'm wondering what thoughts people might have. Yeah, Simona.
Oh, my thought is just the same. Lower horizontal resolution is much cheaper, and a few years ago that was the standard model. So it still is quite a good model, and we have some configurations even with webcam. So you can do good simulations with that, and I think the computer is getting better, so it is getting cheaper relatively, right?
Mm-hmm. And oh, there are lots of hands at this point. Patrick, I assume your hand is kind of a vestigial hand. All right. Cecile.
Yeah, then I agree with what Simon says. It was what we discussed in our group, that people want to have low resolution, and probably low horizontal resolution could be the easiest, or to have a lower top model, but still, who is going to do the tuning? And it's something that we have to keep in mind. And if it's us, we need to have the resources to do it. The resources in terms of people and the resources in terms of computer time. It's not an easy task to tune, even if you go from 1 degree to a 2 degree. We did this for CAM5. I did this with Rich. And then the Wacom group, Mike Mills and other people of the Wacom group did this for CAM6, and it's a big effort. It's not something that's easy.
But it is something that we have thought might be, we have thought in as recently as last year when you came up with a tuning document that the community could start to take over.
Yes, and the
tuning.
and the community can start to take over some aspect of the tuning, but still they will need then computer resources to do this, because it's something that's expensive in terms of people and in terms of computer time.
So right, so it's not just a matter of knowing how to do it, but having the resources. Yeah. Yeah, Colin.
Yeah, so I'll just say I very much agree with what Simone and Cecile said. And I saw that Christine actually posted this in the chat. I think there are potential opportunities. I mean, we've been playing around here with this kind of interpretable optimization strategy. I think there might be ways with machine learning or emulators or things like that. With regard to the I guess, faster model thing, the one thing I would say that we want to be careful of is, I could, for example, tell my students to go run 1 degree CAM4 physics and you get a pretty reasonable climate. I mean, it would be the state of the art climate from, some years ago, but it'd be reasonable. The problem is a lot of times when I hear people say, I want a fast, simple model, then they come to AMWG and they see all these new cool things. And they're like, well, yeah, but why don't we put club in that? Why don't we do X, Y, Z? Why don't we do this? And suddenly it's not a cheap, simple model anymore. So that's the one thing, I guess you have to kind of walk that fine line. You could say, well, go check out CESM 1.2. That's a pretty fast, finite volume kind of bulletproof thing. But then someone will turn around and say, hey, but I want all those bells and whistles you guys have been talking about over the last 5 years. So that's, I guess, like I said, I don't really have an answer for that, but just one thing to consider.
Okay. I mean, I think there's some problems. I don't know, variability is something that keeps coming up as one area where we want full physics that may not be the latest, but is still a real, quote unquote, real model. So okay. But yeah, I see Han Lee has his hand up, and then Adam.
Yeah, it's maybe related, but switch gear a little bit. During the workshop, I've seen, at different places, people talk about scale awareness, scale respecting, parameterization, and also Patrick today mentioned this gray zone project. I'm not very familiar with that, and I don't know what's the plan, or is there a working group on that, or what's the kind of the plan for pushing that forward?
So you're asking if there's sort of a specific subgroup that's dedicated to scale aware or high resolution parameterization?
Yeah, like the Gray Zone project. That's the first time I heard this from Patrick's talk. I was just wondering if there's something going on and that we can participate and contribute to.
I mean, yeah, maybe Adam will comment. I mean, we have efforts that you heard about on parameterization development. I wouldn't say that there's right now an explicit focus on making scale-aware parameterizations that are appropriate for all resolutions. I think our hope is that things like Club MF will be better behaved as we change resolutions. But we don't have an explicit, we don't have an explicit effort to address high resolution parameterization.
Actually, I was thinking that this may be more appropriate for the lower resolution simulations the community is requiring, because if people want to run a lower resolution but still want the kind of the fidelity or the good representation of the physics, that's where you really need this kind of you have a high resolution to help validate the tuning, but this can be applied to lower resolution simulations.
Okay. So Adam, did comment or?
Yeah, so I'm just gonna stick with my original comment. I think that I think we should heed the advice of the software engineers to decommission something, and it's clear to me that the least that the Eulerian die core is something we can get rid of without people coming at us with pitchforks. And so I also think that if we can pump some resources into SCAM, not only will we have a more robust SCAM model that we can use, in particular this type of stuff that Julio and I are working on, where you can force it with 3D model output, but then there's this great benefit that we can decommission the Eulerian die core. And so I just think that that's the lowest hanging fruit to give us some nice benefits and, you know, alleviate the overhead of having this extra die core that nobody really uses.
Yeah, that sounds good. I think probably we'd probably have to get some input before, you know, pulling the plug. I think the same thing may be said for Cam3 physics. But yeah, I don't think what we have now is sustainable. So I agree, and I certainly, not only for software maintenance reasons, but I certainly would love to see an effort to kind of once and for all separate SCAM from the Eulerian die core. There's really no reason that SCAM should be referring to the Eulerian die core for anything. But
yeah, it's an important hierarchical contribution to model development and physical process understanding. So
yeah,
I just think you would get the most bang for our buck if we did that, because we finally get rid of this other headache.
Right.
Okay.
And Steve mentioned Cam3 physics, and frankly, I have to confess, I'm not even sure what Cam3 physics are.
That's Peter's favorite physics package. I don't know. Nobody runs Cam3 physics.
Yeah.
It actually has one good thing. It has a switching time steps. So we discussed earlier today that you had one thing after the other that actually had alterating time step when it did the processes. Otherwise, I wouldn't say too much good about it, but that was actually an interesting feature about that one.
All right, but I still think maybe we can leave it. But
yeah, certainly.
so we are we're approaching 3 o'clock. I myself actually will kind of regretfully ask that we close the session. I do have to leave at 3, but I really thank everyone for their participation. All the speakers, I also want to give a big thanks to, and thanks to everyone for the discussion. And yeah, I think we have some good ideas about where to go in terms of what we might decommission, et cetera, and lots of other useful input. So thanks to everyone, and I hope everyone's I hope eventually we'll get to see people in person, maybe in June. Who knows? I haven't heard anything either optimistic or pessimistic, but that seems to be just the way it is these days. So thanks everyone, and have a good afternoon or evening, night. Thank you. Bye.
Thank you, Julio.
Bye-bye. Good night. Thank you very much. Thanks.
Guys. Bye.
And I see Elizabeth saying in the chat that we are still waiting on a decision for in-person workshop.
For the workshop?
Yeah.
For the
workshop, I guess, in June, correct?
What was
Elizabeth?
decided? We're remote, no?
Not for June yet. We're still waiting to hear what UCAR is going to allow.
Hope so.
I think they will not allow us, but I don't know.
I don't know.
I don't want to put my hope too high.
They'll just allow Elizabeth to go in the room, and that's it.
It will be me and Elizabeth. Okay.
No, thank you. I would rather just stay here then. Thanks. I keep asking. I ask Bokan. We ask JF. JF asks, everyone that will listen. I have a meeting with the people that run the multimedia at Center Green, just so that I can prepare, because I have so many questions, so just, oh, wait a minute.